Oh, hey everybody. Today we're going to be talking about basics of animation programming. Um, Let me know if the volume and stuff is okay. It's been a while since I've done this, so I'll adjust as needed. Cool. So basically today will be mostly a brain dump. I have slides, 100 of them or something. But it's kind of a topic where it's hard to explain some concepts without referencing others that I haven't explained yet. So it's a little tricky at times. That's why I think it'll be more of a freeform discussion. So I'm going to cover a bunch of different topics today. And at the end of each topic, I'm going to basically do a little question section where if anybody has questions, they can ask, or just ask them in the chat. And I'll be checking the chat the whole way through. And I will just discuss whatever questions, clarify points if stuff seems confusing or doesn't make sense. Just poke me and I'll explain it in more detail. With this kind of thing, because you're so deep into something, I might have blind spots about something that I think is obvious and it really isn't. So just poke me and I'll do what I didn't do last time, and I'll repeat the question just in case the chat doesn't make it through with the recording afterwards. So I think that said, we can start. And I didn't take into account that the webcam might actually block the text, because let's see if I can just do this, will probably be safer. All right, so I'll do a bit of an introduction. I didn't do that last time because it was more of a topic where it was what's the word, it was a kind of hobby project. It wasn't something that I've entirely used in production, that kind of thing. Whereas with the animation, I feel a bit more comfortable. So I've been working in animation now for around 9 years. I've worked with 3 different animation systems that were existing. And when I mean worked, I mean in depth. So I've worked with Morpheme, and I've worked with 2 internal Ubisoft ones. I have service level experience with 2 others. And that's more like I've worked with it, but not in depth enough to be able to kind of say internally how things were entirely built to that kind of thing. But I have experience with the high level concepts and some of the internals, but it's not an area where I can say, yeah, I know this thing super well. So in general, I've worked with, say, 3 to 5 production level animation systems. On top of that, I've built 3 separate animation systems in 3 different projects, which were used by the whole team and covering AAA use cases. So we've had tech anims on it, we've had animators, we have gameplay programs and everything. So, and I mean, I built the whole thing from the import pipeline all the way through to the tooling. It wasn't like I just did a bit of it and then handed it off to another team to do different parts. No, I built the whole thing literally from start to finish by myself, since I was the only programmer on the project doing animation. So I've also been very lucky in that I've gotten to solve the same problem multiple times, which basically means that every second or third or fourth or fifth time, whatever, you build the same thing, you'll understand the problem better. And so you can start stripping a lot of the kind of unnecessary complexity because you didn't understand the problem super well. And so as you get more experience, you realize actually all these fancy things that I built, nobody's using them. They're not giving us anything. They're just causing problems in the code, performance, this and that. You just start stripping. And so I'm at the point where I've built an animation graph and animation system 5 times. 3 times it was used, 2 times it wasn't. And so I've kind of evolved the concepts across, and I've also taken the best concepts from other systems. I've also basically built everything that's touching animation in the engine. So as I said, the list is there, like facial, IK, ragdolls, import, retargeting, that kind of everything pretty much. Now, I started in 2011 at IO. I got super lucky at the time because when I started, I wanted to do AI and I wanted to be an AI programmer and stuff. But I got there, and my first week I was on the crowd team for Hitman Absolution. And there was a programmer there called Michael Butner, and he was like, "Oh, well, you seem bright, so port the animation system to PS3." And at that point, I'd never touched a console. I'd never seen a console. I was fresh from South Africa working in enterprise software. And then there was like, oh, SPUs. It was a trial by fire. Somehow I survived. And basically through that connection there, he got me into animation. I kind of been doing that ever since. And at that time, we were doing a lot of kind of more cutting edge stuff. That's where a lot of the motion matching stuff originated. He was sort of the progenitor of that entire field to a large degree. I think it was one of the first most well-known uses of a motion matching approach in games with the Hitman crowd. My first experience with an animation system was Morpheme, which, funnily enough, even back then was way more advanced than a lot of animation systems that I'm seeing people using today, especially in some of the like engines that are out there. It's sort of ridiculous that we're still not at the level that thing was 10 years ago. Now, don't get me wrong, there was a lot of things in Morpheme that could have been improved, but conceptually it was so far ahead of the curve that it was incredible. So I got lucky with having that as a head start. Now, when it comes to animation programming, this is a kind of a black hole of, there's not much information. Most other topics there is info out there. You can look at rendering, there's articles, there's conferences, there's this. You can look at gameplay programming, there's talks at GDC and that kind of thing. Animation fundamentally at the core level is not really discussed. A lot of people still think it's like, oh, it's just sampling and blending and that's an animation system, and that's not true. There's a lot more to it. And the amount of people that actually understand the whole kind of pipeline are very few, and we're shrinking because a lot of people nowadays are becoming more users of what's already there. So an animation programmer is becoming a gameplay programmer that plugs in animations to a large degree or gets the animations to work. And anybody interested in the field is kind of like going out there and trying to look at information. There just isn't much. There's this book, which again I have, so I'm not even pretending. And this book I wouldn't recommend it. I don't know what this is intended for, who this is intended for, but if I look at like some of the sections, they cover everything from particle systems to motion capture to IK to fluid simulation. But the problem is they cover, for example, particle systems is covered in 4 pages, the entire topic. Fluid simulation is 25 pages. Don't waste your money on this. The problem is, apart from that, there's nothing else out there. And that's kind of the motivation of this, is just to give some more info out there. It's like I can't cover everything, but I'll give enough of an overview that maybe it'll nudge you in the right direction. And I'm also, when I move from company to company, I work with new programmers, tech handlers, that I keep seeing the same problems and the same mistakes sort of repeated. And I kind of want to just clear the air on some of that stuff and try to explain it in a simple way that sort of demystifies some of it, especially the concept of root motion. That is something that at every company I've been to has been super confusing for a lot of people. And I hope to just kind of clarify that a little bit today. So, as I said earlier, it's going to be just a brain dump. We're going to cover basic topics, and then we're going to do some best practices kind of thing. What we're going to cover today is basically sort of everything up to the graph and the logic aspect of things. We're going to start with skinning because that's kind of where we have to start. We're going to talk about the concept of a skeleton. You think that's an obvious thing. It's not really, and there's a lot of tricks there. Then we'll talk about animations, like how they're created, how they're stored, how they're sampled, blended, that kind of thing. Then we'll cover the two interesting things I think is more root motion and synchronization. We'll cover events, and at the end, we'll do some procedural adjustments and motion warping. So this should kind of be the foundations of how to basically import an animation, how to read it, what's the data format, that kind of thing, and then what metadata you need on an animation and how to use the animations. I'll do a second stream at some point on the actual how to integrate it into a game and how to do more game use cases with animation. That'll be the more the graphs and those kind of things. It's just there's a lot of stuff to cover, and doing it in one shot I think is just it's insane for me, and it's going to be insane for everybody. You're going to just lose your minds, and I don't want this to be another 2.5 hour stream. So let's just jump right into it. Skinning is sort of the foundation of a lot of the animation stuff, because what we do in games is fundamentally we're just deforming a mesh to kind of fake motion. And how that's built is fundamentally we have a set of positions. These are the bones. That's why they're inverted commas. They're basically just world space transforms. And then what an artist will do is he'll start weighting each vertex in a mesh against those transforms and say, hey, I'll maybe use the linear blend version. Is like, hey, this vertex is actually a blend of this position and this position with some weights and some math calculation. And then as those transforms move in space, the vertices get pulled along with them because they're fundamentally weighted against those transforms. And that's what animation is. It's basically those world transforms moving and dragging the mesh along with it. Now, it's important to know for the renderer, there's no hierarchy, there's no skeleton. It's just world space transforms. And a lot of times they're not even necessarily world space, they're in bind post space, but that's a detail that's kind of irrelevant. If you're interested in that part, you can research it later. But fundamentally, it's just a set of transforms. They're not connected in any way, they have no hierarchy. Skinning also has pretty severe artifacts. So depending the approach that you use to calculate the skinning, there's things, the most common ones is, for example, candy wrapping and skin stretching. If you try to use something like dual quaternion skinning, then you have actually blowouts, like you have more mass created. You have less of a candy wrap, but you have more mass around certain joints exposing out. Some of the approaches, like the center of rotation stuff, will actually have a much higher computational cost as well as a memory cost. There's pros and cons to kind of this, but the fundamental takeaway here is that most of these approaches all have artifacts that cannot be solved purely by the skinning math. So for example, this is like some stuff I got off the web where, the linear blend skinning is the kind of one that's the most common, and pretty much I think a lot of engines are still using it because it's super simple, it's really cheap, it's well understood. There are alternatives, but as I said, they both have their own set of issues. And a lot of the time, no matter what approach we take for the skinning, we have to help the skinning out by basically adding more bones. The more bones you have, the more your weights are sort of distributed along different transforms, and they're not relying on one transform. So if you move like the elbow, like half the arm moves with it. So you put additional bones within the arm that the vertices are bound to, that basically allows them to move independently and sort of kind of decentralize the skinning weights, rather just spread them out across more bones. So what we end up doing is we add a lot of extra bones to the character that aren't necessarily common. Depends about the verts. Kevin's asking whether we also add extra verts. That's more of a artist thing. I can't really speak to that, but sometimes we can add more verts if there's a lot of stretching, but usually you want more bones as well to bind those verts to, because again, if you just add more verts and you have one bone that they're all bound to, it's not going to help necessarily, unless you're trying to exploit a artifact of the skinning, which again, that's more of a implementation detail of like how your artists want to work and how how much they like interesting solutions to problems. So in general, what we do is we add these bones. Like the most common ones are the twist or the roll bones that in the forearm. I don't know, like I think webcam's big enough, but in the forearm we would add intermediate bones here that are not actually, they're usually a child of the elbow. And what they do is they twist independently. So as I turn my arm, they will twist with a percentage of the parent. And what that will do is it'll basically smooth out the rotation of the arm so you don't get the candy wrap. Again, this is a whole topic on its own. But fundamentally, the important thing is to note is that the bones that you think a character has, like a human or half a movement, exist. But additionally, we have a lot of extra bones that are primarily used for deformation and rendering. And that's very important to note. Additionally, some characters these days have these like very crazy parts to their meshes. For example, pauldrons in armor or very rigid pieces that we don't want them to kind of. We've all seen like the knight that bends over and all of his armor starts bending and like twisting and stretching. Sometimes you just don't want that. And so what you want to do is you want to have those pieces stay rigid, and basically you want to orthopose it, saying like, hey, if the shoulder moves forward like this, I need that piece to go into this pose. If my arm like extends out, I need it to lift up and go backwards. So you're basically almost authoring the poses that you want those pieces of the mesh to be in, given as another bone. And we often do this. There's different names for it. Some people call it set-driven key, you know, an RBF solver, that kind of thing. Fundamentally, what it is, it's saying, I'm going to look at my bones, and based on some set of bones, their positions, that will define the positions of other bones. It's like the simplified way of doing it. But it's not like just doing some basic math. It's literally saying, hey, I'm going to just move this thing in this position. And the RBF thing basically is a neural network that you've basically fed in a bunch of poses and you've trained it and saying, like, if you get these inputs, provide these outputs. And the other thing that's important to note is, depending on the mesh, you may have a different set of bones. So for example, in this scenario, it's the same character. In one case, he has a tank top. In the other case, he has a jacket with a stiff collar. The one mesh will have a lot more bones than the other. So that jacket will likely have some sort of an RBF or something for that collar, or some sort of a deformation setup there to help it move properly, not clip, not kind of bend in weird ways, that kind of stuff. Whereas for the tank top, there's probably very little deformation helpers in there. And so the thing is that as I start switching out my character's customization, clothing, whatever, the number of bones will change. And that's super important to note, is that on the rendering side, the number of bones will change a lot. And these days, that change can be very, very significant in terms of numbers. So for example, here we might have 50 bones in the jacket, but only like 10 to 15 in the tank top. And the complexity of those setups will differ. Because again, depending on what that outfit is, you may or may not need extra bones. So these deformation bones, they're generally calculated on the CPU in advance. They have dependencies to other bones in the character. They often need to work in various spaces, and I'll come back to the coordinate spaces later, but they generally need to work in one of many spaces. Sometimes they need to be done in their parent bone space. Sometimes they need to be done in what I call character space. Think of it as world space. They sometimes need hierarchy information. Is it a chain of joints or whatever else? And this is where now you start needing the skeleton concept of a hierarchy, parenting, all that kind of stuff. So when we look at our mesh skeleton, and again, I'm talking purely in the rendering sense. If we look at our mesh skeleton, we have two sets of bones. We have the bones that are used for motion, like the stuff that you would expect a character to have: knees, arms, fingers, spine bones, head, that kind of thing. And then we have all these procedurally calculated deformation bones, which is stuff like, I don't know, left arm roll 1, 2, 3, 4. Right glute RBF 1 to 15 or whatever. These are all just helper bones. When When we do animation, at least character animation on the character, we don't care about these deformation bones. They are completely irrelevant to us. All we care about is the core set of bones that we want to animate, because we don't want to care about what's the character wearing when I'm animating the character. And we want animations to work across multiple meshes. We don't want to have to make an animation per mesh, right? So all animators care about is the core set of bones. As such, what we end up doing is we define a core skeleton per character type. And by skeleton, it's more of a set of proportions. So generally you would have something like an average male, or maybe a small male, or a large female, or maybe it's a bipedal mech, or a horse, or small quadruped, large something along those lines that define basically the set of bones needed, and to some degree their proportions, like hip distances, how many clavicles should they have, those sort of things. And then what an animator will do is they will take that set of bones and they will build a control rig around. And that control rig is basically how they animate. It's a set of tooling to help them animate. And this core skeleton of those bones that is shared across all the meshes, that is your animation skeleton. And this is where there needs to be a big distinction between the two. So before we carry on with that, we also need to talk about gameplay, because sometimes we forget that we make games when we talk about tech, and gameplay is important. And so we have a lot of helper bones that are also added to characters. And those helper bones are generally things that have no skinning to them. They don't affect the skin in any form, anything. They're just fundamentally offsets and attachment points. So if I want to holster a weapon, I would have a holster bone that would basically be where I would attach my gun. Maybe it's on my chest, maybe it's on my hip, or whatever. And that bone is something that gameplay does care about. And granted, the attachment bones is something that might be entirely in the mesh and doesn't have to be in the animation skeleton, but sometimes those need to be animated. In special cases, depending on what I'm wearing, what move I'm in, I need to animate that holster. And if I need to animate it, it needs to go into the animation skeleton. Additionally, we have anchor bones, which are used to kind of basically define a point in the environment that we're interested in interacting with, that's used for warping or those kind of things. We're going to get into that later. Or we have things like IK targets and offsets that we use to solve procedural animation problems. So these are just bones that are in the skeleton that animators will need to animate and place correctly in the scene and, keyframe or whatever. But they don't matter for rendering, if that makes sense. And it's important to note here that rendering and animation at this point have different needs. Rendering just cares about those final world space positions and how to do the skinning, and that's it. And on our side, we basically have to take care of both sort of the gameplay side of anchors and offsets and those sort of things, plus the character motion. That leads us to requiring two different skeletons, right? And the core bones are the same. But the distinction comes in is that the mesh skeleton will then have all these procedural bones or deformation bones, and the gameplay one potentially have a set of gameplay bones. And those two skeleton concepts, they have to be separated out. Now, we're going to talk about why that's super important later on, but first thing to clarify, one thing that people get confused a lot of the time is the bind pose, the reference pose, this sort of thing. The bind pose is the pose that the character rigger or the skin, the tech character artist, what they skinned against. They have a set of default positions for those bones, and what they weighted the vertices against, that is the bind pose. It's the skin binding stage. They bound the verts to these bones with this weight, and the original position of those bones was here, and that's the bind pose. Right? It's primarily used for rendering, because a lot of the time in different skinning approaches, you're using stuff relative to the bind pose. So you need that original set of positions that the vertices were weighted against. Now, in animation, there's also a bind pose, and this is where the confusion comes in. I call it a reference pose just to distinguish it from the bind pose. It is the default bone positions for the animation skeleton. it is not the same as the bind pose, or it doesn't have to be. Some bones might be in the same position, some bones will not be in the same position, because it doesn't matter, because they're solving different problems. And in some cases, they want some bones to be in different positions in the animation bind pose, because they're not animated that often, and they want to keep that fixed offset in every animation. So they'll have the controller basically ignore those bones and just use the reference pose position. And that reference pose position might be different from the bind pose. So that's something to not confuse the two things. The animation reference pose and the bind pose need to be, rest pose, Connor mentions, is another term for it. Rest pose is something that is used as well. Although, again, I've had tech animators and tech character artists confuse rest pose with bind pose all the time. This is a super confusing concept. I don't know how to fix the name. Maybe it's just animation skeleton default pose, mesh skeleton default pose. The animation reference pose is really not used that much in the game. It's sometimes useful, but in general, it's not. The bind pose is the one that's literally used every frame. So the next thing to talk about is multi-pod characters. These days, pretty much every game has customization. You can have different outfits and whatever else. Some games have multi-pod characters, some games don't. Generally, when you want to split the character, you basically take his character and you cut him up into chunks, and you have things like head, torso, legs, or boots, pants, whatever your game requires. The important thing here is that each mesh only contains a subset of the bones needed, and it's only the bones needed to render it. So it's like, if the torso, we want the torso, we're not going to include the legs in that mesh. We're going to just have whatever bones we need for skinning, be it pelvis and up to the neck and clavicles and whatever, plus all of the deformation bones needed to render that mesh. And then when we animate a character, we have a separate animation pose. And this is where, now I haven't covered poses, but we have a set of transforms that the animation that we want to, pose our character specifically. What we then do is we take that animation pose, which again covers all the core bones, and we transfer subsets of it to the different meshes. So for example, we might have a pose that's on an average female skeleton, and then we would transfer that to the head, to the jacket, to the pants, to the blouse. And those will be subsets. And then we would create a mapping of saying, hey, in the animation skeleton, this bone is index 7, and in the head, that index will be 15. And then we'll record that, and then we will do an index to index transfer of transforms. And so we would basically animate, and I'm using the word animate here for the mesh, we would animate each of the meshes individually, but we would also transfer the minimum set of bones needed for each one. And that's the important thing here, is we're just setting the information that each one of those meshes needs. And each one of those meshes contains a subset of those core bones. So Gabriel is asking which one would be in a T-pose. That is also not an easy question to answer, because we have multiple poses. We have the standard Jesus T-pose. We also have a pose that's slightly down like this. It's entirely arbitrary what that pose is. It's whatever the, if we're talking about rendering, it's whatever the character artist finds easiest to skin to. For animation, technically that rest pose, I've seen cases where character artists prefer this, animators prefer this. There's no hard and fast rule. I know back in the day, it was kind of funny that Mobu required everything to be in a T-pose for characterization with Human IK. And so if you were doing like animals, you would have an elephant in a T-pose, and you'd have a tiger in a T-pose, and it would look ridiculous. A horse in a T-pose. Again, it's fundamentally solving different problems. Whatever's easiest for the character artist, that's what they're going to use. So coming back to this, I'm harping on about the same topic for a long time, but it's important because this is one of the biggest fundamental areas of confusion with animation stuff. Different skeletons serve different purposes. They are way, way less animation bones than mesh bones. Way, way less. we also need to split the animation skeleton sometimes in multiple parts. For example, these days, if you're using bones for facial animation, you'll have 280, 300 plus bones in just the face, right? Then let's say you have a body that's maybe 110 bones ish, 100 bones ish. Then maybe you have a cape and that's another 150 bones maybe. And then your weapon, which is God knows how many bones. If you put that in one skeleton, that's like 500, 600 bones. We have characters at work that are 570 bones, mesh bones. We're not animating 570 bones every frame, but that's how many bones in the final mesh. And we need to split that up because, for example, this is a kind of a scenario where, you know, you would have the discrepancy of like 80 bones for the character and your torso and legs is like 240 bones. You know, your animation skeleton for your head and for your mesh may be the same, because when it comes to facial animation, you have the same number of bones, because each one of those little bones that you're animating are the deformation bones in that case, and that's how you're getting your facial animation. So why is it bad to kind of unify these things together? Well, we are basically, for example, facial, we're setting that once a frame. We're not blending facial animations most of the time. We're not doing weird procedural stuff. We're basically saying, okay, you're playing one voice line. We're going to play that facial anim, and that's all we're going to do. And we're going to do that once a frame. Right? We're not going to have characters that are speaking 5 lines at the same time. They usually have one pose. And you can't really blend facial animation. It doesn't work that way. For the cape, it's the same thing. You basically set that once per frame at the end of the frame, and that's either coming purely from animation, or it's coming from your sim, or it's a blend of the two. So there's maybe a couple more operations, but it's not that many. Whereas for your character, we have cases where we do 20, 25 blends per frame when we're doing multiple transitions. And there you want a very small set of bones where all of them are mostly used, so that you can basically have one pose that you know the size. You can basically optimize your operations there. I've seen cases where some engines, they don't make this distinction. They don't split the pose. So your animation pose is 400 and something bones. And so then that's a problem, because every time I do a blend of like a run cycle and a turn, well, now I have to blend 480 bones, but only 80 of them are actually affecting the motion. Leonardo's asking, what is a cape pose? Well, if you have a cape, like a cloak, let's say you're making an RPG that has a big cape, or like a superhero game like Superman with his like cape or whatever, you want to animate that sometimes. And it's just a pose for the cape or the cloak or the, you know, long jacket or something. Generally, it's simulated. It's not something that's hand animated every frame. But yeah, so I've seen things, like I said, in engines where they put hacks into the pose and said, well, now we're going to track per bone. Is it used or is it not? Was it set? Was it not? And when we blend, we're going to do a bunch of, if this is set in the source pose and it's set in the target pose, then we blend it. If it's not set in one pose and set in the other, it just makes everything massively complicated and extremely slow. Whereas if you just split these things up, well, you have the most optimal case. And you don't have conditions in a lot of the operations. You just run through the math and it's super fast. And this is kind of the mistake that I see in a lot of places, is that people either create an Uber skeleton, and one very well-known engine does this. They have these monster Uber skeletons, and then they start doing multiple levels of trying to unfuck the mess by creating compact poses and then creating a separate pose for the mesh to try to reduce how much they send to the GPU. And it adds a lot of complexity. Instead of saying, hey, this is my animation skeleton, these are the bones that I'm animating, and that's all there is. And if you want extra stuff, you do it as attachments, which have their own skeletons, and your character will have multiple animation updates per frame, but each animation update is light and small and does the bare minimum it needs to do, and that's it. It also has bigger wins for memory. As I said, 480 bones, if you have a whole bunch of those poses, it's kind of shitty. It's a lot of memory wasted for stuff that's just set to the idle pose. Kevin is asking how are the two skeletons authored. They're generally well, feel free to ask questions. That's the point. The two skeletons, they're generally authored by two different teams. So the animation team and the character team will sync up at one point and say, hey, these are the proportions our character has. They'll define the set of core bones. Then animation will create a control rig and an animation skeleton. The render skeleton doesn't technically need to exist. It doesn't need to exist as an asset because it's never fundamentally used. And what I mean by an asset is a shared asset across multiple meshes. Each mesh can have its own skeleton embedded in it because that is essentially what's going to happen with the deformation bones and stuff. So you don't have the concept of a render skeleton as an asset on disk, whereas the animation skeleton is an asset on disk because it says, hey, when I'm animating an average female, these are the bones that are animated. These are the tracks that I know exist. This is how much memory I would need for a pose. It also allows you to simplify your decompression. It can optimize your sampling, your blending, all of that kind of stuff. Is the animation always a subset? Yes. If you want to animate a character, it has to be. Now, the rendering skeleton. So, yes and no. Technically, the rendering skeleton can exclude bones that are in your animation skeleton if it doesn't need them. There are cases where, for example, you do an LOD on a mesh skeleton and you start stripping away finger bones or whatever. Yeah, you have it in the animation. They're there, but you're not setting them on the render skeleton. So it's technically a Venn diagram of bones, I think is probably the best way to describe it. What I generally do is on a mesh component, I would flag the animation skeleton that's intended to be used, and then I would generate a mapping from that animation skeleton to that mesh that's used. And then when I set a pose, I will transfer the bones that exist. And then I would run the procedural bones and everything else to fix in between stuff, if that makes sense. There are situations where it gets more advanced, where, for example, your mesh may have more intermediate bones than your animation skeleton. Maybe you have 3 bones in your animation skeleton for the spine, but then your render mesh is super complex and now you need 8 or 9. And so what you would do is you would have the 3 bones that would have the pose transferred, and then you'll procedurally calculate the intermediate chains. This is similar to what the Destiny guys were doing with their compression mechanism, their character rigs. The idea is that if you split the two, you have a lot more freedom to decide what you want to do. And, you know, at that point, it's more of a programmer can fuck around a bit and come up with some good ideas or whatever there. But you don't fundamentally mess with your anim data every time the mesh changes, or your mesh data every time the animation changes. That makes sense. It also allows you sometimes, if you have the animation skeleton and these separate skeletons, you can generate pose pools for those types and say, okay, I know that I'm using currently average female, horse, and heavy male. And those 3 are the skeletons I'm currently loading and using. I can create a pose pool. I can even create one per thread. And then when I'm doing any animation operations per thread, I will just hit that pose pool and not alloc memory. So for example, my animation graph system doesn't alloc at runtime. Everything is pre-allocated. And I'm pulling data that's already there. So I try to minimize the amount of allocations per frame I do, which again is important for performance. So another best practice, and this is a mistake that I've seen a lot of places. These deformation bones, they're not just bones. While essentially when they get past the renderer, they're just bones. But they need to be procedurally animated, and each one of those bones has a different set of operations to run it. Twist bones need to have a twist operation running. If it's a poke, there's a different set of math. If it's an RBF, we have to run an RBF solver. If it's a look at, we have to generate the look at. And each one of those look ats might have a different bone to look at, a different percentage. How much weight must the twist take of the parent, and those sort of things. There's a whole definition for how those deformation bones need to be solved. And this is where sometimes I've seen some kind of crazy things. Some engines say, well, that's an animation problem. It's not rendering. Fuck it. And so you need to set up a separate sort of animation graph, animation setup per mesh to animate these bones. And now whenever you switch the mesh, you have to switch that graph and say, okay, this mesh needs to go with this animation setup, and you have to link this thing. And it's horrific, and it's a super tedious and error-prone way of doing this. It also means that people can make mistakes. People can forget to set the settings correctly. Every time the mesh changes, they have to update those anim setups, and it's just a mess. What I tend to do, and what I've done every time I've built these systems, is I package the deformation as well as cloth, which I'm not going to touch on much today, within the meshes. So each mesh drags along its deformation setups and its cloth setups. And this is coming primarily from the DCC, from Maya or Max or whatever motion builder, where the animator there will define, or sorry, the character artist will define the set of operations. They will preview them in the DCC. They'll make sure the weights are working. They'll make sure the skinning's there. They'll have their entire workflow there, and they'll hit one button, and then it'll spit out the mesh plus the entire setup for all these deformation bones, all the RBF weights, all the neural network training, whatever needs to be done. And in the engine, you have a single asset that has everything needed to render it. So whenever you say, hey, use this mesh, it comes in with the deformation bones, the LOD settings, everything just works. It's like, boom, it's there, it works. You don't need to have now data tables of saying, oh, this mesh and this anim setup and this mesh and this thing, and which is stuff that I've seen, and it's a massive, massive pain in the ass. And again, programmers and designers shouldn't have to care about what the hell set of deformation bones I need to run for this mesh, right? They just want to say, I just put on this piece of armor, this like piece of clothing. So that's the end of the skinning part. Are there any questions before I move on to the animation section? I guess not. Okay. So we'll move on. Again, if you have any questions that doesn't have to be necessarily exactly about the stuff I covered or in general about that topic or whatever, please ask them. As I said, I don't know if I'm going to cover everything in enough detail, or even if you just want to ask something that you've seen or whatever else, maybe I can give you some insight on it. So let's just make this a bit more freeform than me just blathering through these slides. Okay, so the actual animation part. So now I can define what a pose is, even though I mentioned it earlier. So a pose is just a set of transforms for the bones in a skeleton. And as we said, we have the two use cases. We have an animation pose and we have the render pose. An animation basically is just a sequence of poses that played sequentially will produce motion. So that's kind of the best definition I could come up with. Our animation data within that pose basically is okay, there's a question saying, do you have to structure skeletons in a tree? Do you mean multiple skeletons or which part? The skeleton itself is a directed graph. It's a graph with no cycles. That's kind of the essence. You have a single root bone, and then you have basically a tree of bones coming out of it. That you kind of have to do, and I'll explain why a bit later. But actual different separate skeletons, they don't need to be linked in any way or anything like that. So coming back to the pose, each transform in the pose has three components to it: translation, rotation, scale. That's kind of standard stuff, and that's what we animate. When we get to the DCC side of things, how animators work with those. Sorry, let's see, there's some questions. I'll come back to this. Okay, so deformation setup is actually a set of bones and how to deal with them that goes on top of core bones and finds the full scale. Yes, the deformation setup is a set of bones that are children of the animation skeleton or have their own structure within that skeleton. And yes, there's a setup that basically says how each bone should be procedurally animated. It's like saying, in my arm, I'm going to put in a bunch of twist bones, and this twist bone needs to take 80% of the rotation of the elbow. This one needs to take 60% of the elbow, and this one needs to take 30% of the elbow. That setup is defined, and then when I am about to render the mesh, I'll set the animation pose, which will fundamentally move the elbow and the wrist. It'll move the arm somehow. And then I'll say, cool, I've got my animation pose set, run the deformation bones. And then it will say, okay, based on the current pose of the elbow, this bone should be in this position, this bone should be in this position. And then we send that off to the renderer. That answers Marco's question, which is as to how they handled. So they handled as a post-process once the entire animation update runs. They're literally the last thing that happens at the end of the frame. Just before we submit to the renderer to say, hey, by the way, your mesh is now fully updated. There you go. This is also a nice decoupling because different LODs will have different deformation helpers. So LOD 0 might have a very complex RBF and shit tons of deformation bones because it's in a cinematic and we zoom super up close and we want to see pistons and stuff move if it's a mechanical thing. But in game, when it's an LOD 1, we don't need any of that stuff. So we would have a different set of deformation bones, and we would have a different setup for deformation bones, which if you're trying to build an anim graph for this is a fucking nightmare, because now you have to say, oh, LOD 1 is this thing, and LOD 0 is this, and LOD 2 is this, and anytime anybody changes a mesh, you have to redo that whole thing. It's a nightmare, and then you have to hope to God that the engine does whatever you have in the DCC, if you even have preview in the DCC, which it's a horrific workflow. The best thing to do is have it all in DCC so the character artist can see it immediately and they can tweak it and they can kind of get a really, really fast iteration workflow. And then your engine must just be basically a viewer for that whole setup. Jack's asking what RBF. RBF stands for radial basis function. It's just one technique used to basically control complex setups of bones. For example, a pauldron or something, you want to say, I want it in several different poses. It's just a technique that's used. You can Google it and stuff. There's ways of doing it. It was just an example that's commonly used these days. Marco says, I see the export is more complex than I thought. That's kind of a mistake that a lot of people make, but historically that's worked because our skeletons were like 20 bones, 30 bones. Nowadays, when they're 560 and we have all these super, super complex setups, it doesn't scale anymore. And when every single like torso mesh is a completely different set of deformation bones, it's a nightmare to do that inside the engine. And it's better just to bundle everything up, and also you don't want to have your character team crying because that workflow is just back and forth constantly. Okay, so coming back to the animation stuff, I touched on this earlier. Basically, an animator will take that set of core bones, that animation skeleton, and they will build a set of tools on top of that set of bones called a control rig. That's basically just helpers saying, oh, if I move this bone and I'm in IK mode, I need you to solve the rest of the chain or whatever. This is entirely dependent on their stuff in the DCC. They build what they need and how they want to work. And that's completely separate from what happens in the engine. So it's entirely their kind of domain and they build what they need. And what they do with that control rig is they basically create sequential poses is the simplest way to describe it. Under the hood, what ends up happening is per bone, you have the various components in individual tracks. So you have the X rotation, Y rotation, Z rotation, X rotation, scale. They're separate tracks. And under the hood, that control rig will generate those poses, which will generate curves. And so for each one of those components, there will be a curve under the hood. And what the animators are fundamentally doing is they're just authoring these curves. And that's the animation of that component over time. Frame rate is something that's an arbitrary value, especially in games. Basically, it's like saying we want to have keyframes at these frames. That makes sense for, let's say, movie and film, where you're pretty much going to see those frames because you are rendering it out at that frame rate, and you're going to play it back at that frame rate. But in games, we almost never play back at that frame rate because we have variable time steps. So for us, we're pretty much always in between those curves. So for us, that's sort of kind of irrelevant. The other thing is when they author those keyframes, they can also control the interpolation between them. And this is sometimes we can get into a bit of trouble where they might decide that they don't need a bunch of keyframes, and they'll author a fancy interpolation curve that basically covers a whole range of frames. That can cause issues. Most of the time it's fine, but sometimes it can cause issue. But the important thing to note here is that in the DCC, the data is curves and it's split per channel, right? So it's not like a transform that's being manipulated. It's individual components that then get composed into a single transform for rendering, export, whatever. Well, actually, if you're using FBX, they stay curves. If you use something like GLTF or some of the others, then at that point they get resampled and spat out as keyframes or something. Although I think GLTF these days supports curves. I haven't really kept up to date. Now, when we import that animation, we do something very different here. We actually take those curves out of the FBX file and we sample that animation at a specific frame rate. We say, okay, I want to do it at, if it was authored at 30, I'll sample at 30 ideally. Ideally, we will sample it at what it was authored at. That way we will get those exact keyframes that they have created. Then we will take those keyframes, those poses. So we'll sample the pose at every step of that. We'll take that data and then we will compress it into a runtime format. What that runtime format is entirely dependent on your compression scheme. The two most common approaches are curve fitting, where it stays as a curve. And we try to create a different curve that will sort of match the animation data that we have. So we basically try to generate a single curve that covers the whole animation, but it's going to be lossy because it's not going to be the exact values. Or we basically just say we're going to just quantize the individual poses, which basically means you take the pose and you basically compress the pose. I wrote up a big blog post on this, so if you want more information on compression, I'm not going to do that here. You can just Google literally an idiot's guide to animation compression and you'll get to my blog post. It covers a lot of the concepts. It also covers, it has a reference to a lot of different articles that give more information. And this is kind of a implementation detail. It doesn't necessarily matter. When we want to read that animation, so now we've imported it, we've sampled those keyframes, we've compressed it down. Now we want to play it back. So what we do is we say, okay, as I said earlier, we're almost never at an exact keyframe. There's a question, thoughts on variable bitrate? Personally, I'm kind of skeptical on a lot of, well, not skeptical. I think that these days with the amount of memory that's available, it's not really necessary to do these super lossy approaches. So for example, at work, we have something like, I don't know, 40,000 animations or something in the game. And that takes like, trying to remember the numbers, but it's something like maybe 400 megs compressed. And I'm doing like a very dumb compression of I'm literally just taking the poses and quantizing them. No variable bit rate, 48 bits per quad, 16 bits per translation, whatever. The dumbest possible thing you could do. And we have, I think 400 megs for 40,000 animations is good. We're not loading all of it at any time anyways. And frankly, these days with like our 10, 12, 13 gigs, if somebody says to me, your animation budget is 150 megs, it's like, no, I mean like 4K textures and you already blown my animation budget. So it's like, we have the memory. We shouldn't be butchering the animations these days like we used to. We used to do horrible things like we would sample at 7 FPS, 11 FPS, and not 30 just to reduce the memory. And it would cause some really horrible things. We don't need to do that anymore. So when sampling, As I said, we're not at any exact keyframe because as the engine steps, it's stepping at a variable time step most of the time. And even if you've locked your frame rate, it's not guaranteed that it's going to be exactly 30 FPS all the time. So what ends up happening is you have a starting point in an animation, like in the diagram, and then you have the end point of the animation in the diagram. And that's what was covered in terms of time on that animation for that frame. And so what we end up doing is when we just want the pose at the end. And so we say, okay, at the end time, we're at like 0.44 seconds in the animation. What keyframe is that? What frame is that? Oh, it's like, I don't know, what would it be in this case? Like 12.6 or something. Okay, so then we say, well, it's 12.6, so I need to get, for example, I'm assuming that it's the compression is pose to pose and not some curve fitting. As I said, this is more dependent on compression. But I'll use the simple example. It says, okay, well, we're at 12.6, so I need pose 12 and I need pose 13, and then I'm going to blend between 12 to 13 at 60%. And there, that's my pose. It's a relatively simple, and when I say blend, I mean interpolate. So it's generally a slurp or a lerp on the translation scale. I'll cover the blending later, but basically you're just taking the in-between of those two. But that takes us to blending. Sorry, I'm just gonna have to clear my throat. My allergies are killing me the last couple of days. So this is the meat of most animation systems. Pretty much, you can basically boil down gameplay animation to sampling and blending. Fundamentally, that's all we do. And we have, and a blend is just an interpolation over time. And when I say over time, it just means that we're saying, when we blend poses, there's no time involved. It's pose to pose, you blend. But when we blend with animations, we generally say, I have one animation, I have another animation, and then I want to overlap them and I want to blend from one to the other. And that's the general blending case in games, where we're blending over time, where we will start at the source animation at 100%, target at 0, and then we will slowly ramp the one down and increase the other and blend in between. We have fundamentally two types of blending. There's not really a name for the default blending. I'm calling it interpolative because it interpolates. I don't know if there's a better name for it. That's kind of what I use. And then we have additive blending. Before we cover the blending and the interpolative additive, I need to cover the spaces. This is something I haven't touched on. And this is important. This is another big point of confusion. When working in animation, you have three spaces. Mostly in games, you think about local space and you think about world space, or local global, or what is it, object and world. The naming gets confusing, and in some engines it's local and world, you know, when it should be local global and object world. But anyways, so these names are arbitrary. There are three spaces. The bone parent space. This is the space of relative to a bone. So if I have my wrist and it's parented to the elbow, bone parent space is the wrist relative to the elbow. It's the offset from the elbow, right? Then we have character space. Now what character space is, each character has a root bone. That's the root of the skeleton. It is everything relative to that root bone. So that, imagine that root bone is the origin of the scene. Everything is relative to that root bone. I call it character space because it is in the space of the character. There's no forward, left, right. It's just my character mesh, everything relative to it. And then we have world space, which is what you would expect. It's basically character space in the world, if that makes sense. This is sometimes referred to as global in the DCCs. And this is where a lot of the confusion comes in. In the DCC, local means bone, global means world. They don't have the concept of character because everything's relative to the scene origin, which is, you know, it's not a game engine. It's a different kind of problem space. And that's important to note. So for example, when you're building a character hierarchy in a game, you would have your capsule maybe, and then you'll have your mesh attached to the capsule, and that mesh position defines your character space. Why do we need character coordinate? Okay, so the question is, why do we need a character coordinate space? I'm going to try to act stuff out, and this is going to be interesting. DCC, the question is, what is a DCC? A DCC is digital content creation. It's basically the authoring software like Maya, Blender, Max. Sorry, I'm used to using those terms. There's a lot of terminology we use and we take for granted. So character space is useful because when I want to express certain desires or intentions, it's useful to have a space that isn't dependent on my orientation in the world. So if I want to say I want to turn 45 degrees, right? I want to go 45 degrees to the left. What is left if I'm in world space, right? If I'm flying a ship, what is left at this point? Is it world left? Is it left according to my cockpit? Is it, you know, that concept goes away. Whereas in character space, I have a well-defined space that I know conceptually, this is my character, 45 left is, you know, within this angle. Generally, our character, when we have him in the rest pose, you know, we have the Jesus pose or whatever, it's like, yeah, we have a forward that's defined. We have left and right that's defined. We have offsets that we can reason about. So if I say 2 meters up, I know that's about head height or whatever, a little bit above head height. You know, I have context for what character space is. So when we do a lot of operations like IK, we generally do them in character space, especially weapon holding, anything like that, because the weapon is relative to the character. So we say, okay, well, your weapon is at this point in character space. I'll just do it in that. Additionally, it can have benefits in terms of accuracy. For floating point math and stuff, you generally don't want very large float numbers. The accuracy decreases. And if your character is very far in the world somewhere, you don't want to use that math to calculate IK and any procedural stuff. So what you want to do is you want to basically say, okay, relative to the character, my offsets and stuff are going to be generally smaller, right? Instead of being at 2 kilometers out in the world and everything's now done in like kilometers and meters and whatever, you know, like I have half a meter offset from the ground, so it's a 0.5 float. Those are kind of the reasons why this is necessary. Also, it's easier to express things like velocities, orientation, and stuff in character space as an offset of my forward. Sorry, that was a long-winded way of saying like that. Sorry. All right. So the other important thing is when we do animation, we generally store poses in bone space. I'm going to refer to things in the simplest term: character, bone, and world. No local, global, which is going to be confusing. There's multiple reasons why we do this. The simplest one, the easiest one to the first kind of thing is that if I modify the parent, it modifies the children, which is kind of obvious. So if I rotate the elbow, my arm goes with it. So I can pose my arm and I can then rotate it. That's beneficial because we don't necessarily want to recalculate everything individually and set them always in global. We just want to say, okay, you know what, just rotate the arm, the shoulder. That's kind of simple. It's also a lot easier to apply procedural adjustments. So for example, if I'm doing, let's say I have like I'm doing a shooter game and I want to have a variable height for the character that will adjust according to covers and whatever. I can offset the pelvis and move the whole character up and down. And then I get the feet or whatever. So I just move one transform and then that moves the whole character. So that's super easy and super beneficial. Additionally, when it comes to blending, it's really important because, you know, if you blend globally without keeping stuff locally, you will lose spherical movements and you will have issues with the bone length preservation. So here's an example of that. I should have drawn this better, but imagine we're blending from the bottommost position to the topmost position, and the orange bone line is the result. So we're going from the bottom to the top. If we just do that in global space, when we do the interpolation, we're going to end up at halfway through, we're going to end up there because that is the halfway point. But now that bone has shrunk. right? So that path in space has now been linearly interpolated, which is not what we want, right? Because your character will start shrinking and stretching and weird things will happen. So generally what we do is we just want to rotate that bone and keep the translation, keep everything in place. So I hope that's sort of clear. And this kind of thing comes into, I'm going to mention it again a bit later, but it's also important for, sometimes we have like very complex helper setups inside of our animation skeletons for weapon handling and stuff. And this is super important there because we need those IK helper paths or whatever to make sense. And so we do a lot of kind of extra chaining of bones to provide clean and smooth paths when we blend, which we can't do if it was just global. So when we create the render pose, as I said, that the deformation bones, they need both stuff in bone space as well as in character space or world space. So generally what ends up happening is you work fundamentally in character and bone space. You do all your procedural generation for the kind of deformation bones, you calculate everything, and then you apply the world transform, put it into world space, and then you probably do another step relative to your skinning algorithm, what you need to do to submit that to the renderer. For LBS, it's converted relative to bind pose and then sent down the pipe. We generally stay in local space during the entire pipeline for animation. We almost always stay in bone space. The only time we ever need to go into character or what I call global is for certain operations where we need to do some IK, we need global positions of bones to calculate new targets or whatever else, or for the deformation bones. So, but it's a very special case scenario where you need this. I hope this is readable. The font might be a bit small. This is my API from my pose in my hobby engine. The stuff I've built in the past is very similar to this, but fundamentally a pose is a very simple concept. What it is it's an array of transforms, the local ones, the bone space, and potentially an array of global transforms, a skeleton, and then some state. The idea being is that when I want the global transforms, it's if I'm accessing 2 or 3 of them, it's generally just faster just to calculate the whole pose, because if those things are leaf transforms, I might just end up doing most of the operations anyways. So, and usually when you need one global space position, you probably need a second and a third and a fourth, and it just ends up sometimes you're just saying, okay, calculate the global pose, and then I will just have a cache of it. But again, that's an optional thing if you want it or not. It's good to have a state within the pose to know, hey, is this a reference pose? Is this a zero pose? Is this an invalid pose? Or is it an additive? Or what is this thing? Because that can give you, again, optimization opportunities of saying, well, if somebody calls reset on the pose and it's already somebody says set it to reference and it's already a reference, I don't need to do anything, and those kind of things. And again, it's a very simple API. It's a very simple concept. It doesn't need to be more complicated to this. Unfortunately, most engines I've worked in, it's not like this. There is classes of machinery, of concepts, of templates, of God knows what, because they're trying to solve the render problem, the animation problem, the compression problem, everything in one place, and it becomes a mess. So just getting the list of transforms can be a fucking pain in the ass sometimes. Whereas it's as simple as just saying, I have an animation, I say get pose, add a frame, boom, I have my pose, I'm done. That is what it should be. So coming back to blending, this is a very, very simple concept. All we do is we blend from one transform to another with a percentage between them. Translation scale is generally lerped, and rotation is generally slurped, which is a spherical lerp. Now, there are articles out there that say, hey, use a normalized lerp, which is a cheaper, different technique for this, but it has a discrepancies in the velocity, it's non-uniform, and a bunch of other things. This can be problematic if your frame rate is spiking or if it's low. Additionally, again, those articles will say, hey, it's not a problem, nobody's going to see it, blah, blah, blah. Yeah, maybe in, like 10 years ago, it was maybe not an issue when we have like 10 bones. But if I have a massively deep hierarchy or I'm trying to calculate IK targets and now this thing is speeding up and slowing down halfway through, and all of a sudden my IK is going fast, slow, fast, it's an issue. And these days, it's not really that much of a performance concern as back in the day that this is necessary. When we come to the additive blending, what additive blending is basically applying an offset to a pose. So instead of blending from one pose to another by interpolating between them, you're basically taking a base pose and you're taking another additive pose, which is just offsets. And then you're basically applying those offsets with weight. Right? It's simply saying like, hey, if I have at my base, we're just going to do simple numbers 10, and then I want to add 5 onto it, but I want 20% of that 5, so I'll only add 1, and now I have 11. That makes sense. That's all it actually is. How these poses are created is actually the exact opposite operation. They have a pose, they have another pose, and inside of their DCC or in the engine at import time, you just subtract the one from the other and you calculate the offsets. This is primarily used for modifying procedural bones. For procedurally modifying poses. So for example, you would have something like, maybe you have a pose like this with a gun. And then you apply an additive offset on the spine, which will bring up the character or shrink them down, or that kind of thing. Or you would additively adjust the aim point. It's primarily used to just offset portions of the pose. That makes sense. So, blending. Again, this is a very, very simple thing. You don't need to overthink it. It's not complex. It's not rocket science. It is literally what you see there is that is the blend. It's like 6 lines of code and you have your entire fucking blending for your animation system. Pretty much. The final thing when it comes to blending is a concept called a bone mask. What a bone mask is simply just a weight per bone. That's it. It's all the bones in the skeleton plus a weight. And again, these bone masks are only used when we're blending. So all you're basically saying is that when I blend one thing to another, I want to use this bone mask to apply an additional weight to things. For example, I want to blend 2 poses together, but I only want to blend the upper part of the second pose. So I will have a 0 weight for everything below the waist. And then what you're going to get is you're going to get 100% of the source pose's bottom half, and then you're going to get the blend of the source pose's upper half with the target pose's upper half. This is fundamentally useful for layering, whether additive or not. So for example, I might have a run cycle where the character is just running. And then on top of that, I want to now do a reload while running. I don't want to lose the walk cycle. So what I'll do is I'll layer on the reload, but I'll probably do it from the waist up. So I'm going to play this animation, which was probably authored, like standing straight up. It would, it's just something here. You're manipulating the gun, you're doing something. There's no animation below the waist. And then what you would do is you would blend that on top of a walk cycle with a bone mask. Generally, the question is the bone mask something you need custom tooling for? Yeah. How they're defined in my case is in the graph. When they want to use a bone mask, they click a button and a bone mask editor pops up. And it gives them multiple ways of editing the bone mask. They have a little human character that they can just say left arm 10% or whatever. They also have a per bone way of setting the weights and a bunch of other tooling. Fundamentally, all they want to do is they want to say, for this skeleton, what are the bones that need to be flagged at which weight? Now, the tricky thing is that the bone masks are shared across skeletons. So well, in the animation graph, they're shared across skeletons. You can branch them out and say make them individual per skeleton and variation, whatever. I'll get to that once we get to the graph. But fundamentally, you just want to cover parts of the body, right? They don't really necessarily care as much about the individual weights. They want to say, hey, I want the shoulder to be at 100% and I want the wrist to be at 60% or 20%. And everything in between, I need you to just feather it, which basically, 60, 40, 50, whatever, 60, 50, 40, 20, whatever. This again is dependent on how your tech animators are working and what your needs are, but yeah, you just need a basic bone mask editor. It's your very first version could literally be every single bone with a float entry next to it. And then you can improve that later on. So the final thing to blending, here's an example of the actual entire blend function. I have two poses, a weight, a bone mask, and the result. There's your blend. That is all the code you need to blend something. They use those blender functions above. That's why there's a bit of a template to basically just pick the function to call. And that's it. That's all you need. My entire blending sampling code is probably like 200 lines of code. It's not a major thing. We have another concept. As I said, you generally don't want to do stuff globally when you blend things. There are use cases for this. They're rare, but they do exist. Generally, only do this if you really, really need to. For example, there was a talk years ago from Assassin's Creed where they basically they want to layer a wave. So they have a character standing upright doing this. But then they have a character that's kind of like walking a bit hunched over. They're like this kind of thing. If you layer the arm onto that pose, you're going to end up with, sorry, I'm going to try to get in frame. You're going to end up with this, right? Which is not what you want, right? That's not a wave. That's DJing, So what you want to do is you want to blend some parts of that globally. You want to blend the global positions of that arm with the body. So what you want is you want this pose blended on top of this one. And so you end up with a wave that's kind of upright. So instead of the arm being down here and doing this, you end up having it up here. That makes sense. Again, the use cases for this are rare. I'm not entirely sure if we've even used this option on this project. We used it in the previous one, but in this one, I'm not sure anybody's ever ticked that box. So it's a tool to have, but not a common one. That covers the animation format. The next thing I think we're covering is the root motion. So if there's any questions, let me know. The question is, you mentioned before that using more than one thread for the animated games usually have a budget for it bigger than one thread. So animation is a massive cost sometimes. Depending on how many characters you have, it can be a lot of characters to animate per frame. My animation system is entirely parallelized, so it doesn't run on the main thread at all. You basically just set the control parameters, you let it run. It's not super expensive. It costs something around, trying to remember the newer numbers, but let's say 40 microseconds for the graph evaluation, and maybe another, depending what the operations are involved, maybe another 50 to 70 micro, assuming I'm not running a ragdoll or crazy IK. So it's not a lot. It's like, call it 100 microseconds per character. But then if I have 100 characters, that adds up. So generally you want to parallelize this, and there's no reason not to parallelize it. Both the graph logic, all the animation stuff, none of it needs to run the main thread. So all of that is updated. Kevin's asking, have you ever made a bone mask library top half only left? So that's what I said with a little character picture. They have presets where they would basically have a little picture that glows in green and red depending on the weight. And then you have presets that you pick, full body, left arm, upper body, whatever. And it sets some initial weights, and then they can then tweak if they need to. This is a kind of a thing that it depends on how often you need it and how much tooling you want to invest in, all those kind of things. That one's pretty much a UX UI problem to solve. Depends, entirely on your team and what they want and how they want to work. And yeah, there's a lot of depth in animation. And as I said, I was hoping this wouldn't be a very long one, but it looks like it might be. There is a lot of kind of depth here, and there's very little information out there on it. SOA to AO. Okay, the question is thoughts on SOA versus AOS for the blending. Well, there's no structs and there's no arrays. I have 80 transforms that I need to blend with 80 transforms. I have both of those. As soon as I hit the first on both arrays, I have the rest in cache likely, especially these days with Ryzen with their insane like 200 megs of cache or whatever the hell the latest ones have. As soon as you hit the two poses, just referencing them in the blend, you have probably that data in the cache already, and you just iterating through it linearly. So it's pretty much the best option for that. There's nothing to optimize there. Cool. So root motion, and this is the topic that I think is the most confusing for everybody. Every company I've been in, every place I've been in, this has always been the one concept that confuses people the most. And I think fundamentally it's because a lot of programmers themselves don't understand it. And so when they try to explain it, they butcher it. And so it just makes things way more confusing than it needs to be. So this also has so many fucking names. At every company, it's a different name because the root bone is called something different. It's called the ground, the displacement, the root, the character bone, the pedestal, I'm trying to remember other names that I've seen. The pivot, what have you. It has just various names. So let's explain what it actually is. All skeletons have a single root. That should be sort of explanatory. If you have a tree, there's a single starting point for it. That root will define the position of the character in the scene. So if I apply a will transform to a skeleton, everything will be relative to that root bone because everything's a child of the root bone. So that root bone is the position of that mesh character in the scene. If I move that root bone, the whole character goes with it. Again, it's the parent. That should be simple enough to understand. In games, generally characters are defined by a capsule or some other physics object that is the position of that entity in the world. The character position is generally the capsule position, the floor of the capsule, the bottom position of the capsule. And it's not the mesh's position necessarily. It's the root bone is set to the bottom of the capsule. That's where the character is, and we move it around. So the root is always at the bottom of the capsule. What that implies is that the root bone is where the capsule is. So, i.e., the root bone is the character position in the game. Wherever the root is, that's where the character capsule is. That's where the game thinks the character is. Whatever the orientation of the root, that is what the game thinks is the orientation of the character, irrespective of what the mesh is doing. The mesh could be doing somersaults, but if the root bone is left in one place with some orientation, that's what the game thinks the character is. And I think that is what's not explained to people, is that where that bone is where the character is. When we move characters in games, we have two ways of doing it. We can do it with code, which basically means that the capsule is moved by code directly. Code just says set position, boom, there's the capsule moved. The animation doesn't move. The animation doesn't move the capsule in any way. It tries to match. You move the capsule, you figure out, okay, I move this frame with 10 meters a second in this direction, whatever, you feed it to the animation system. It then tries to match and plays a walk cycle or whatever. It will not match exactly because it cannot match exactly, right? Because your animation is built to some metrics, your movement is different metrics, your frame rate varies, You have collisions, you have friction, whatever. So it will never match. So there will be some sliding. When you go the alternate route where the animation defines how the capsule should move, what ends up happening is you basically try to predict where you want the capsule to be, and I'll cover this a bit more in detail. You say, okay, I think the capsule should go here. You tell the animation system does some calculation, says, actually, I've moved you here instead, which is maybe a shorter distance or further distance or slightly to the left, whatever. It gives you back the actual distance moved by the animation. And then you move the capsule with that. And this matches the animation because it's coming from the animation. And there's generally no sliding. Does that make sense? Marco is asking, well, he's saying that he's thinking in regards to be able to pull the transform in vector registers easily, given that each blend is completely, well, in my case, my transforms are already using vector registers. Everything's aligned. Everything is M128 types. It is supposed to be vectorized. So my operations are just basically some intrinsics when I do a blend. So Connor is asking, if a character hunches, would you need to animate root forward? Ha! Funny you asked that. I will cover that literally in a slide or two. Anthony is asking, is there a reason to pick the bottom of the capsule instead of the center, which would map to the... Yes, there is. And this drives me nuts in Unreal because they have the character position at the center of the capsule. Well, depends on the game, but most of the time we have characters that walk, and I need to know where the ground is. And having to constantly minus the capsule half height in all of my game code is a massive pain in the ass, especially given that our meshes are authored in a way that the root of the mesh is at the feet 90% of the time, because in the scene, it's at the origin a lot of the time. So what ends up happening is you have, for example, in Unreal, you have your capsule with the center at the middle, and then you have to put a minus capsule half height offset in the blueprint to move the mesh to the floor so that it actually the feet align with the bottom of the capsule. Most engines have the character position at the bottom of the capsule. Yeah, Unreal is annoying, and as far as I know, it's the only one I've seen that ever does this. When you're working with AI especially, it is a even worse pain in the ass because you're dealing with the nav mesh there. And there you pretty much always want the ground position of the character. You never want the hips. It's game code never cares about the hips, ever. They don't care. It's just like you move a capsule, it shoots, whatever. They don't care about the hips, how many bones in skeleton, what the pose is. They usually, it's irrelevant. So when we animate a character, the animator can choose where that root bone is. And this is where a lot of the problems start coming in. So again, I'm repeating that the root bone is where the capsule is. If you can, ask your animators to create a debug visualization in the DCC, in Maya or whatever, where they can see the capsule and have that capsule attached to that root bone so that they can literally see the capsule in their DCC and give them some presets saying, well, my capsule size when crouched is this, when it's standing, it's this, whatever. Just so they can visualize where the capsule will be, where the character is. Because to Connor's question, when we crouch or when we're on the ground or something like that, the placement of the capsule defines the physics collision. Right? So that's the thing that actually collides with the world and walls, trees, whatever. If the character sticks out of that capsule, which they often do because a lot of people don't understand where that root position should be relative to the mesh, we end up with situations like in that example where half the character sticks out the front of the thing. And that's why in games you'll see when you're crawling or something, your head will be half in the wall, or when you're crouched, like you'll clip through everything. Those are relatively easy to fix, both through widening the capsule a bit and positioning that root in a sensible position based on the movement. If I've got a walk cycle and I'm crouched, that root should probably be leading the character a little bit, just so that when I collide, my mesh is behind, right? It shouldn't be back where the hips are, because then the entire front half of the character will likely stick out of the capsule and it's going to go through walls and stuff. This is the cause of a lot of the clipping. Sometimes the capsule is a lot narrower than the character, and so it clips. So the question is, Yes, the intersection of animation, collision, and gameplay code sounds like a whole other can of worms. Yeah, it generally is. And the problem these days is we don't have a lot of people that understand the interoperation of those systems. And so it generally becomes a lot of sort of reinventing the wheel because some people maybe understand one aspect but not the other. And then it's, everybody's trying to kind of collaborate. And without that experience, without understanding how each piece works, it's problematic. Well, you might want the capsule center for 3D pathfinding when pathing in SVO. Well, your pathing and your actual movement, they don't need to be related. And yeah, if you're doing like 3D pathing, maybe it makes sense. But if you have something that's flying, your route probably isn't going to be on the ground, right? And maybe your capsule won't be a capsule because let's say I have a spaceship. I can't really define that with a capsule, right? Your physics object might be completely different at that point. Do I prefer gameplay or animation? I'm going to touch on that a bit later. That's a whole topic of its own. I'm going to just briefly touch on here, but that's also a massive can of worms. Yeah, so I guess I animated the slide. You'll forgive me if I've forgotten what I've done with some of these slides. But yeah, the idea is that where you move that thing, it defines where the capsule is, defines your collision response. Another thing that's important to note with the root bone is since it's the root of the hierarchy, it acts as the blend pivot. Since we blend in local space, everything is relative to its parent, and its parent, and its parent, all the way down to the root. So when we blend poses, we blend around the pivot. So if we look at this situation here where we have two characters in exactly the same pose, they just have different offsets from their root. So what ends up happening is when you blend here, you'll see a slide. And that is because there is an offset between the root and the pelvis. And this is kind of one of the things that's a giant pain in the ass when you start doing a lot of Anim-driven stuff. In general, if you're doing root motion, having to maintain that offset correctly between poses and in transition. So generally what they would do is they would copy a pose with the root offset, paste it at the start of their new animation, and then make it fit with the rest of the animation. Now, you need to kind of keep that in mind and not forget that it is the blend pivot. And you can use that information later on in interesting ways. What was this? Okay. Another case is that when they animate, they can leave that root at the origin of the scene if they want to, right? It's a separate bone. It doesn't really mean anything. They could, in Max, just stick it at the origin, move the character, hit export, boom, you have an animation. That's generally not a good idea because now the character will walk through walls or whatever it's in its way, and the game will think it's a different position and all these kind of issues. If you animate the root to move with the character, well, you get the capsule and the character generally moving together. What we generally do with the root motion is so in this example here, this means that the animator, every frame when he made a keyframe, he put that root where he thinks it should be. And then as the animation plays, the root also moves with the character. When we import an animation, what we end up doing is we extract that motion out into a separate track. We basically strip it out of the root, and then we set the root bone to identity for every frame in the animation so that the character is always relative to the origin. It's basically like we're counter animating it. Once we extract that root motion track, we then also modify it so that the first transform in that root motion is at the origin at 0, 0, 0. Might seem silly to do that, but a lot of times animators will animate in a scene at like 10 kilometers off into the distance, right? Because that's how the scene was set up, whatever. And then you get an animation and the first frame is at like, Timbuktu somewhere. So we always basically bring it back to the origin. So our root motion track always starts at 0, 0, 0. So what we end up doing is like, when we separate this out into the separate track, that basically allows us to now use it in both code-driven or Anim-driven, because we have the choice of, I know how this character moves. I have the root motion, I can extract that data and I can apply that movement if I need it. But if I don't want it, well, I have a character pose that is relative to the origin, so it's running in place, basically, right? So I still have all the animation, but it's not moving in the scene. So now I can move that via code if I need to. That gives us kind of the best of both worlds. We have both root motion, we have the ability to do it code-driven, and that's kind of what we need to do. We shouldn't have this mode where, for example, again, I'm going to use a reel as an example, but their root motion is kind of a second-class citizen. And there you have to explicitly extract the root motion and all this kind of stuff. And they don't even have a separate bone for this, which is super important, as I'm going to cover into this. There, they literally take the root and they basically counter-animate it out. So we've talked about how we sample poses. Sampling the root motion is pretty much the exact same thing. There's a time update. We know where we were. We know where we ended up in time on the animation. The only difference here is we need to take the position that we were in at the start and the position that we were at the end and calculate the delta between them. We just want to calculate how much we moved, right? And then we take how much we moved and we just move the capsule with that amount. So if I did 1 frame of motion and I have an animation that covers, I don't know, 20 centimeters per frame, I extract that out the root motion, I apply that to the capsule, and then the capsule and the animation will match one by one. We pretty much always work with the deltas, and that will become apparent a little later, but that's kind of the important difference here, where we don't sample just the end, we need how much did we cover, and then once you loop, that becomes a bit tricky because you have to keep that in mind and all those kind of things. The question, why not use a set of key bones to define a capsule volume and build the capsule from the actual position of the bones? You can't do that because you cannot build metrics in your levels. Generally, what we do is we define a capsule that says, okay, our characters are 45 centimeters wide, 1.8 meters tall or something. And then all levels are built to that capsule dimension, saying that I can now guarantee that this capsule has to fit through all the doorways. I need to provide space for 2 characters. And I have a very fixed size for my metrics for the level designer. So I can basically tell them, this is the size of the character, this is how much space needs to be available. When it crouches, it's now 1.6 meters tall, now 1.8. Your covers need to be this high, blah, blah, blah. And then they can build a level and check the metrics. We also don't want this capsule randomly scaling based on pose. Because at that point, like, there might be a gap that works for one character, but now another character gets stuck and all these kind of issues. We do change capsule sizes based on state. That is something we do, but that is, again, purely a gameplay feature. Where, for example, when we hang, we want to shrink the capsule a bit, or when we crouch, we shorten it, make it wider, those kind of things. We do that, but that is all done in gameplay code and via designers and stuff. I think the best way to think of animation is, think of it as a skin. If I remove the animation, the game should still function, even though I just have a capsule floating around the scene. That's how you need to think of it, is you have the game, which is a capsule, everything's built around it, and the animation is just visual candy on top. So, blending root motion. Again, you can Google this. I did a blog post on this. Just Google blending animation root motion. There's a quick 1-pager on it. It's not super complex. The most important thing there, again, is we're working with a delta, right? So it's not 2 transforms that you blend. It's 2 deltas that you need to blend. So you need to handle that a bit differently. Kevin is asking, doesn't metrics also include movement speed, and level designers know how long? Yeah, exactly. So the metrics will define how fast the capsule moves, how high it jumps, a lot of these things. We'll have metrics for, okay, we can climb between 1 meter and 4 meters. Do not make a 5-meter thing because we don't have coverage animation-wise. Or don't make walls that are in a weird dead zone that I don't have a climb and I don't have a vault over, those kind of things. We have metrics for speeds, we have metrics for heights, we have metrics for widths. Whether they get respected or not, that's a whole nother discussion. But in theory, we have metrics, and that's what we build our levels towards. And again, if you're prototyping, I would always go code-driven with a capsule, fuck animation, and prototype your gameplay, your movement, your everything, and make sure that feels good, and then build the animation on top of that because it makes everybody's life easier, because you can give the animators a reference, say, hey, this is what feels good. How do we make animations to match this sort of motion that we want to do? Right? That's better than saying, well, make animations, we'll make this thing at the same time, we'll somehow figure out how to glue these things together and make it unified, which is generally just asking for pain. And yes, root motion can be a pain for that, so we're going to touch on that in a bit. So root motion has additional uses, and apart from just moving a character. It's also very useful to understand what an animation does. So that can be used for selecting an animation, or I don't know why it says scaling. I meant warping. Basically, when we extract the root motion track, as I said, it's pulled out into a separate uncompressed track that just has the positions of the character at every frame in that animation. Again, relative to 0. So from that, what you can extract is you can extract the average velocity. You can extract the total displacement. You can get exactly where the character ends up with what orientation, and other metrics you can pull out of that curve, that root motion track. This can be super useful saying, hey, I have 20 animations to reach a point. Which one is the best one to pick, right? To some degree, this is how a lot of these motion matching approaches are. Now, my memory is a bit fuzzy. I don't remember if it's motion fields or motion graphs, but one of them was that you're giving in, hey, I need to be sort of in this position, orientation, whatever, and it would pick an animation based on the root motion or whatever. There's a lot of information you can extract out of the root motion that is super useful for you to simplify your graph setups. And again, a lot of people don't do this, and so their graph setups become really, really complicated because they just don't leverage the information that they can already do. And I think a lot of the reasons why people got burnt on graphs was fundamentally because their graphs become super complex because they try to brute force solution to problems where this may be a slightly more elegant approach. Kevin says, playing back animations 1.2 speed to match the player speed. Ironically, we do that a lot, actually, even with root motion. I think the rule of thumb is something like 15-20% is unnoticeable. You just run the animation slower, faster. It's generally not something you will pick up on. Anything past that starts to get a bit funny. Again, depends on the animation. But the rule of thumb is 20% is roughly the upper limit of how much you can scale. So we have to do that because a lot of times the root motion isn't exact, right? We say 500 meters a second and we get back an animation that's like 480 or something, and then we have to kind of scale it to roughly match the metrics. So we do that a lot in many cases. When you're doing networking, sometimes it's also necessary to speed up animations. You want to basically say, okay, I need to catch up, so I need to run this at double speed or something, or 20% faster or something, because you're trying to take into account some of the lag, and so you're not constantly catching up. Although that is a whole nother can of worms. Well, you say PS2. Kevin says, I've seen PS2 games that do a ramp up by scaling the playback tick with the character speed. I'm not sure which one of the Uncharted. I think it might have been Uncharted 3. Try to walk, like just feather the stick, and you're gonna literally see slow motion, right? Because they were just speed scaling the animation. And it's super funny to see, but also it doesn't really matter because almost nobody's doing that anyways, unless it's probably a dev trying to fuck with it. They pick their battles smartly. So now the next bit is going to be how to author the root motion, because this is actually kind of painful for a lot of people. I would specify, I would suggest that you ask the animators to create a separate object in their scene. That's not part of the skeleton. That is now a separate thing, call it whatever you want, character, ground, root, whatever. And have them be able to animate this as they need. Because a lot of times they might need to make adjustments to the root motion, but they don't want to fuck around with the character pose. The animation is perfect. All they want to do is they want to adjust the root motion to be better or to suit the gameplay needs a bit better. So a lot of times they just want to mess with that, and you don't want to now have to build constraints and counter animate and God knows whatever else you do. Just have a separate null object or something that you can animate. Then when you import, what you would do is you would rebase your animation to that null. So you would basically ignore the original root of your character, if you even have one, or you would make the pelvis relative to that. And in the importer, you would handle that whole switch. So basically in the importer, you would make that the root of your character, and then you would extract the root motion from that. It sounds complicated. It's just one or two transform operations. This generally simplifies the problem, and it allows them to sort of prototype a bit better without having to like invest in a lot in control retooling and that kind of thing. Andreas asks, what do I think about procedural animation? Like, no, I think procedural animation has its place. It could be really cool. It depends on the type of game. If you're doing something like Overgrowth, where it's cartoony and stylized, and it's it's like an indie title, and it's kind of like a lot of sort of kind of attacks, and how do I put it? The quality expectations are not super high. It's more feasible there, and I think that we're going to see a lot more usage of that. We're already seeing a lot of it for IK, aim grids, all this kind of stuff. A lot of it is procedural. But when it comes to actual character animation, and it's sort of a AAA or something, you just cannot do that because you can't procedurally generate walk cycles that look good or realistic. Right? You can get close. You know, it's that uncanny valley. You can get close. But then if you want to say, hey, this character has a different style to this character that has a different style to this character, I don't know how you would do that procedurally and have it look good and have it look distinct and have it, you know, impart some sort of like characteristics in it. You know, it's a tool in the toolbox that is valuable, but it's not a silver bullet. Cool. So animators will basically say, hey, the root motion is annoying to author. I don't want to do it. Can we just automate this? Right? And so somebody will come up with the idea, hey, let's take the pelvis and we're going to project it onto the floor and boom, we're done. Root motion solved. Don't do this. It just never works. It never fucking works. And if you want to even fuck around with this approach, don't use the pelvis, use spine 3 or 4, because then you have built-in smoothing. Because if you use the pelvis is swinging left and right and popping left and right and whatever else. As you go up the hierarchy, we have stabilization around our heads. We're almost like chickens, just worse. The higher up you go in the hierarchy, the smoother the motion is. Again, it's not ideal. Don't do this. But what you end up happening is, like if you author the root, you say, okay, good, I want the character to run in a straight line, no problem. Now you project the pelvis or something onto the ground, and you say, cool, let's see what that does, right? And that's what we end up with, right? We end up with this kind of jitter. And that is a massive pain in the ass, especially if you want to interrupt that and blend out at some point, because now your root offset from your character is, who knows? It's wherever the hell that pelvis was for that frame when it was projected. It can also cause problems because your orientation and stuff can swing wildly because your hips are constantly turning when you're running. Also, it creates uneven velocities at times where, depending how the character's moving and stuff, you get really weird kind of speed up, slow down, which is expected to some degree, but it doesn't need to be that extreme as a projection would give you. So generally what ends up happening is we have this tool, it gets used, people complain, animators have to go back and reanimate it anyways. It's just a waste of every time. Just animate it to begin with. Now, this gets even worse when we have really complex animations. 180 turns, crazy melee attacks. A lot of times we want explicit control of where the capsule is during those moves. We also want to extract the motion, as I mentioned earlier, and say, look, what is this attack doing? Is this a straight attack that's going 10 meters? If your root is doing this the whole way, what's the actual distance covered? Because there's the distance covered, there's the total displacement. You start having all these kind of headaches. And at which point you blend out, now your character could have a strange orientation. In all my time, I have never seen this work. this projection thing. And yet on every project we try it, it fails, and then people have to go back and clean it up anyway. So just educate the animators and try to save them some pain and some effort, because it's, you know, yeah, I get the appeal of trying to automate stuff, but honestly, it's like some things just have to be done manually. I'll explain this a little bit deeper. Let's say this is a movement animation, right? We swing the hips. Let's say I project spine forward, it's a bit smoother, we get this motion, and that's what we end up with. Can you see the problem here? Right? It looks okay, right? What if I draw a straight line? Well, if that's a run cycle, and I'm driven, my character is going to run to the left. Even though I'm running straight, it's going to start going left, right? I will not be able to run in a straight line. And that is a problem, because even if they get the poses to match at the end, which they will probably, I have leftward movement. And then somebody's going to complain. We're going to have to go back. We're going to have to hand animate it to be a straight line, and that's an issue. Additionally, if we have a really complex attack, especially one that chains multiple movements, we might end up with something like this. And that's not an exaggeration. I've seen much worse than this. And now I can't reason about what this attack is doing, right? Because there's just so much stuff in there. It's literally could be like 3 punches in a row straight, but the character is twisting halfway through it. And this is what we end up with. And once this is projected, put into the game, and the capsule's following this path, we now have a bunch of issues because it clips a wall on the left side at the extreme edge, and now the whole animation gets blocked, or the character gets stuck on a wall or something. This is super important for people to understand that that path is where the capsule will go. So do not use it like with the hips or whatever else. And as you said earlier with the crouch thing, while where the capsule relative to the mesh is, that needs to be humanly controlled and authored in a sensible way for that motion. Additionally, if I need to cancel this somewhere through, I'm going to end up here at some orientation, right? So I attack forward, maybe I can cancel the attack, and all of a sudden now my character's facing at a 45-degree angle. That feels shitty. This animation has an additional problem, is at the end, you'll see there's an orientation in there. Again, if I do an attack, and after every attack my character turns to the left, it's going to be super frustrating for the player. And they're going to start complaining that something feels off, something feels clunky. I don't understand what's happening. So again, this is something where I keep saying that we need to do it by hand. Now, I mentioned earlier that the root is the blend pivot. This can be super useful at times if you're doing like a more slower, higher fidelity game where you really want to feel the heaviness of the characters, you really want to feel the quality, you want to go all out on this, and it's not some crazy superhero I can do like 15 actions at once and jump, like whatever. You can kind of exploit the root as a way to improve your animations. So imagine we have a character that runs and then they want to do a slide, like a 180 slide to change direction and push off and go back. Sort of like a sports, like a soccer player or something. They run, they slide a bit, and then they push off and they go in a different direction. If you have that root for that animation where it slides, go with the character and end up roughly where that foot is, the foot that pushes off. At that point, if you rotate, you add procedural rotation at that point, you will rotate the character around the foot, and then you will launch off that foot. If you don't do that and you have that capsule sitting in the center of the character, you're going to rotate the whole character around that capsule. And at that point, it's going to look like a massive amount of foot sliding. The back foot's going to slide off somewhere. The front foot's going to slide off. The whole character is going to look like it's floating. Whereas if you put that root in the back foot, it's going to pivot on the back foot and it's going to look a lot more believable. This unfortunately has the downside of because that capsule has now been animated to a specific point, blending out at that point, everything has to take into account that the capsule will be at that weird position and not relative to like the center of the character or somewhere else. So there's some considerations there, but if you need to like really, really push your quality, this is a nice technique to do. There's additional techniques where you can adjust blend pivots at runtime, but they tend to be complicated and expensive. But this is a very cheap way to do it if you have 1 or 2 use cases for this. Any questions on this? Oh my god, this is going to be 3 hours. All right, cool. I'll continue and I'll try to speed it up so I don't waste more of your afternoon. Coming to the code versus anim driven. Well, here I mentioned already, the one code drives the capsule. Animation is a skin that follows. Now, the main thing here is that you have a character controller that basically does the character collision checks, the physics and everything. So that moves the capsule once. Based on that movement, we take the velocities, angular rotation, everything, we feed that into animation. It tries to do the best it can, spits out a pose, boom, we're done. It's super easy to iterate on character movement because it's all code. You have a high reactivity because you can do whatever you want. Again, code. There's no realism. It doesn't have to match animations. It's literally whatever you want it to be, Mario style, bouncing up and down super fast. It can have the downside of feeling slidey and weightless. Again, because you're not respecting what the animations are doing, that's out of the downside. So the alternative is that we would run animation driven, which basically means we will extract the motion for the character out of the animation, which is the root motion. What we do here is the character controller will predict where it thinks the capsule needs to be. So it will run the physics, it will run the collision checks, it will move the capsule and say, hey, I think you need to be here. We will take that data, we would feed it into the animation system, it would run, it would then spit out a root motion delta and says, okay, I know you wanted me to be here, but this is what I could do instead, because I was starting a move and I had to do an acceleration and whatever. And then we take that delta and we feed it back to the character controller and say, hey, you need to do this movement. And then this movement will be run against the collision and physics and everything again. So we run the collision checks twice per frame, per character. And then again, the reason why we use a delta is because we say, okay, I need you to move 20 centimeters forward and rotate 10 degrees to right. And then we run collision, and collision only says, oh, you can only move 15 because the animation overshot the desires of the prediction. The prediction said move 10, animation said move 15. We want to make sure that the animation doesn't stick us inside of a wall or something. And I've gone all blurry. Let me see if I can just fix that. Technology. Yeah, all right. So those are the two differences between Anim and code. Animation driven, it will give you the highest quality. The problem is that your iteration times will be a mess. Because if you've started to author your root motion, you've made all your animations at a specific speed and specific velocities and everything, and now you want to change that, you have to go through and change all those animations. You can use speed scaling and a bunch of stuff there to help with this. But again, if you want the highest quality, those animations have to be changed. Anthony's asking if there's a way to improve reaction time. That. So it's not that reaction time is bad with animation driven. It doesn't need to be. The issue is that animators need to understand that they are the ones in control of reaction time and reactivity and how it feels. And that is sometimes sort of orthogonal to their desire to make the prettiest animation. Because now they want to make a pretty animation, which is kind of longer, it has settles, it has really cool subtle movements, secondary motion, a bunch of stuff. The problem is we need that thing to be like super snappy, or we need that stop to stop on the spot. Even if I'm going 5 meters a second, I let go of the stick, I need to stop instantly. Realistically, if you mocap that, well, you need a meter and a bit to stop. That feels shitty. So now you have to compromise and say, look, we need to stop as close as you can to zero. Your mocap is 1.5 meters. We cannot afford that. You have to bring it back. And so there's a lot of kind of compromising that has to happen on both sides. If your tech editing team understands this and understands the implication of this, and they can push back onto direction and say, hey, I know that we want to do these super cool animations, but we're concerned about the reactivity aspect. That conversation needs to happen there hand in hand. Animation driven is not necessarily non-reactive. It can be super snappy, it can be super like reactive. It just needs to be animated that way, if that makes sense. On the flip side, if you change your character movement with code driven and your animations are not updated, then you just have a fucking ice capades in your game, which a lot of games end up doing because I'm assuming they tweak stuff towards the end and the animations weren't adjusted, and so everything just slides everywhere. Which one to choose? Well, it depends on what you're making. If you're making a Mario, probably you don't want to be doing anim driven. If you're making a super polished, like Plague's Tale, kind of like super immersive, super higher quality, slower story game, anim driven can be a great way to like bound your characters to the world and give them weight and heaviness and make them feel part of it. Right? It depends on what you're trying to do. It also depends on the technical skill of your animation team. Again, if you have a team that understands the implications of the anim driven and how it works and like how to author the root motion, that kind of stuff, it's generally okay to go that route. It'll give us the highest quality, but you have to be super careful about the cost of this. Also, I would highly recommend that you do not start a prototyping phase with anim driven. It is a nightmare. Make sure that all your prototyping, when you're trying to figure out how the game is built, how the character should feel, metrics, speed, sizes, everything, that should all be code. And then later on in the project, when you're now like locked down on this is the game we're making, this is how the characters feel, this is it, then start like investing in anim driven animations and stuff just to match your existing metrics, and it becomes an easier task because you have a clear rule set of saying, hey, this is what we need to do, anim, it's your show now, make the best fucking animations you can come up with within these metrics. If you don't do that, then everybody's set up to lose. You know, you're basically just setting up everybody to fail. Also, in your tech, do not make root motion a second-class citizen. That's why in my case, like the Anim system supports root motion. It samples it, but you don't have to use it. It's up to you. It's there. It's always available. It's always there. It's always authored, but whether you use it or not, it's entirely up to you. Any questions on this one? Cool. We're almost at the end. Sorry again about the length on this. So we're going to talk about events and synchronization. These days with animations, you need to put a lot of metadata in them. And you also need to basically synchronize a lot of things together. And we're going to get into that thing. These are very... Whoa, sorry about that. OBS decided to disconnect for some reason. Cool. All right. No, it's maybe it's my internet. So you basically need a way to annotate your animations. This is basically just adding markup on the timeline. So in my home engine, it looks something like this. At work, we have something similar. It's a very simple way. You just basically, it's like almost like a sequence. So you basically say, hey, I just need to put some flags here. There's two types of events that I generally use. There's the duration ones. They're the ones that are multi-frame. And then we have the immediate, which is literally like, if you encounter this event, it happened. Otherwise, it's like it's done. It's a single frame. I don't want to say single frame because it doesn't last a frame. It's just a zero duration instant event. Again, this is my opinion, but events should be just data. There should be zero logic associated with them. They are just information, nothing else. I know some engines, the events actually have code and they trigger code and God knows when it runs and how it runs and what it does. It shouldn't be that way. They're just metadata. they need to be complex types. They can't just be some ID. I know in some of the original versions of Morpheme, event IDs, what all you could put in an event track was an int. And so like we had to hand out basically a Bible to all the animators with a list of 23 is left foot down, 24 is right foot down, 27 is spawn VFX, 29 is, it was horrible. They need to be complex types. You need to be able to say, hey, I need to spawn a particle system here. This is the particle system. These are the settings. This is the offset, blah. Or, hey, this is a left foot event and this is a right foot event and this is ID 16. You know, just it needs to be a complex data that has everything you would need to kind of handle this. Oh, that's not what I said. I just said that the events themselves shouldn't be triggering things when they're sampled and that they themselves shouldn't be running code. Yeah. So I still handle them. I'll show you how I handle them. They're just not handled as, oh, you hit these 5 things, so trigger a call, like, you know, call execute on each one of these events, which I think is how the notifies in Unreal used to work. I'm not sure if they still do it that way, but they used to be basically like if you hit a notify, it fires and it does some stuff. That's not what happens in my case. Also, in my case, like the events are authored in tracks, but when my animation is compiled, they're flattened out into a single ordered array. So basically, also it's contiguous. So all my elements in a single block of memory. So as I sample, I can just, you know, everything's sequential in the cache and sampling them is super cheap. How do we sample? Well, it's very similar to the root motion. We have the start point, and we have the end point. And we basically just create a little time range and say any events within this time range, that's what we return as the sampled events. And the sample events basically have some additional data. They have what animation did this event come from? What's the event pointer? Like the actual data for the event, like what does it contain? What's the weight of the event? What percentage through that event are we in? And some extra metadata, like, and I'll cover that now. So the event weight is basically how important is this event for this update? It always starts at 100%. So we sample an animation, we get an event, it's 100% weight. If we blend that animation with another animation, and that animation also has events, and the source animation is at 50%, the target is the source is at like 30% and the target is at 70, then the events from the source animation become 30%, and the events from the target animation have a weight of 70%. It basically tells us how important and how much of a contribution that animation that this event came from had in the overall pose of the frame. So it gives us extra information about, is this really relevant or is this from an animation that's like got a tiny contribution and maybe not super important? The percentage to the event, this is only relevant for duration events. It's where did our time update? So if we go back to the slide, where did our endpoint end during that event? Was it like 20% through the event, 50, 60? This is important because it can tell us like how far through an event. If it's a very long event, it does something like, hey, I want a particle system on for this amount of time. We know how much time is left, what point we're in, all that kind of information. Again, it's super useful to have. Additionally, we have metadata that can be flagged on these sampled events. And this can be stuff like, is this event ignored? So when we do layering, and I'll get to that when I do the graph talk, we might want to say, hey, in this layer, I want all events from this layer to be ignored. And so we will still sample the events. They will come through. They will just have a flag that says, hey, this thing occurred, but it's been flagged to be ignored. Then we have the branch state. It's basically telling us, let's say we're in one graph state and we're sampling some animations, and then we transition to another. Let's say we were idle and now we're going to moving. As we do that transition, we have 2 branches. We have the inactive branch and we have the active branch, what we're going towards and what we're leaving. If events are sampled in the inactive branch, we flag it and say, hey, this came from an inactive event. We're leaving that branch. So be aware that these are not relevant because we are transitioning away from this potentially. So maybe don't handle them or whatever. And this is how we handle events. And this is where we still have a code handler, but at the end of each frame, we basically take all the events and we forward it to a set of different consumers. Each consumer basically subscribes saying, hey, I need to listen to events of type, cloth, VFX, whatever, damage, footsteps, whatever. And each frame they get sent, hey, these are all the events of this type that occurred. Do something with it. And then it's up to that consumer to decide, what do I do with these events? And it's at that point you can take a look at holistically saying, this is everything that happened in the frame. What should I do with that information? What state is the character in? Am I in a high enough LOD to trigger VFX? Or if I'm not in a high enough LOD, maybe I shouldn't. You have all the logic in one simple function that basically just says, for all events, do something. And at that place, you can put all your rules there and it becomes a much simpler problem. And then you can take a look at stuff like, what's the weight? Is it ignored? Is it from an active branch? Do I have 4 of them? One thing that happens a lot is we have contact events for sounds, which are placed on feet, for example. And if we sometimes blend animations together, like continuously, we will get double events. We will get like maybe 3 left foot down events in the same frame, right? We'll get 3 right foot down events a few frames later. You don't want to fire 3 sounds. You want to fire 1 sound. So you take all those and you say, okay, I've got 3 left foot down events. I'll take the highest weight one, and that's the one I'll trigger. You need to be able to reason about everything that's happened and handle it accordingly. And that's why I say they shouldn't just be an execute function on the event that does something. Other places these events are used, so it's not only the consumers that use it, other systems can also access that information. So a lot of times we want to know, hey, did we reach a specific point in the animation? For example, like I'm doing a big ground slam and at a specific point in the animation, I want to trigger a area of an effect damage. Well, there's an event that basically just has an ID that says do damage or something. The game code can listen and say, hey, if I got an event with this ID, this frame, I can now trigger my thing. Or, hey, am I in the run cycle? Or have I reached a point where I can leave the animation and interrupt status, whatever. So there's a lot of this information that can be given back directly to game code, or it's used directly by the animation system to trigger transitions or to block transitions. You want to say, hey, while I'm in this section of the animation, do not transition. And then the graph will basically say, yeah, okay, I've been told transition. The animation is telling me to wait, I'll wait, and at the end, I'll kick out. It gives you a lot of flexibility and sort of like conditional stuff. So Connor's saying no modification on the event time in a blend, just whichever frame. Pretty much. Nothing gets modified in the events get sampled. They get sampled at a specific time in the animation, everything. That's fixed, that's const. The only thing we change is like how important they are at the end of the thing, and that goes to the blends, because sometimes if you're triggering a transition, like a chain of transitions, you may have animations that have like, depending on that frame, like 0.05% of the actual pose is that animation. Now you don't want to be triggering events from that. It's probably irrelevant, right? And so that's where that information is kind of relevant. It's tied to how much that animation that the event came from contributes to the final pose of the character. Now, synchronization, this is a topic that it's this one is the one that kind of boggles my mind a bit, where a lot of engines don't have a simple solution for this even today, which is just, I don't understand that it's such a simple concept. And yet there's not a solution, whereas Morpheme 10 years ago had a solution for this. And I don't understand why we are where we are today with this. It's like we haven't learned anything. Basically, the problem is I have maybe a walk cycle and I have a jog cycle. I want to blend between the walk and the jog smoothly because I want to go to jog, or I want to be halfway in between the two because they're made to blend. Well, I want to have the foot phases match, but the animations obviously are different lengths and the strides are different and everything's different because they're different animations. The one is a run, the one's a jog or a walk or whatever. I want the feet phases to match for that duration of that blend when I'm going from one to the other, or if I'm halfway in between, I need them to scale accordingly in terms of time, distance, everything. So basically all this is you controlling the time and the speed at which the animations are played and that's it. And this is really, really simple to do with some basic markups. So let's say we author a footstep. So we say, okay, I want to mark up my different phases in the animation. I have a left foot down, right foot passing, right foot down, left foot passing. Cool. I can then basically right click on that track and say, hey, make this the sync track. So any track can be the sync track. It just says, I'm going to specify some intervals that are synchronization periods, and that's it. It just says this one in this case has 4 periods, and that's it. For humans, we mostly use the feet, but in some animations we want to do it, and I'll show you use cases where this is super cool to use, and it gives you a lot of flexibility really easily. So unsynchronized, this is what happens. If we play these two animations and we try to blend them, they run at different speeds, and obviously you're going to get a mess of like whatever the blend's going to be. What you want to do instead is you want to sync the periods. So you want to say, if I'm 5% through this period, I want to be 5% through the appropriate period in the other one. And so you basically run the cursor at the same speed as on both animations. And that generally results in a good blend if the animations are made in a way that it's intended for this to happen. So conceptually, this is really simple, right? All you're doing is you're saying, I'm picking a master animation, and I'm saying, I'm going to just follow the time interval for that animation. Wherever that green line is, I'm going to find the appropriate place in the run, and that's where I'm going to blend to. So yeah, that's the thing. Connor's saying he works with a system like this for transitions, but I don't think it supports blends. I don't know why it wouldn't. It's right. It's relatively simple. It even works when they don't have equal sets of periods. So let's say we have this scenario where we have one track with 6 periods and one track with 2. All we do is we create a separate set of virtual periods. So now we have the same number. And we basically make a virtual length on the animation. We say, okay, now the virtual length is 0.9. It was a 0.3. We've tripled it. Cool. And then again, we basically synchronize the time between each period. And we say, okay, cool, this is the sync. Period 4 will match that virtual period over there. And as the weight increases from track A to track B, let's say we're doing a blend across, we're going from one state to another, or maybe we leave it at something. At 0 weight, the length of the resulting animation, because that blend will generate conceptually a new animation with a new length and new timing. At weight of 0.3, that will be the length. 0.6, that will be the length. At full, we go that. And that's how the synchronization blend works. It's simple is the only explanation I can give you for this. I mean, this takes maybe an afternoon to implement, which is, again, surprising why this is just not common in engines. The other thing sync tracks can be super useful for is to initialize the start time of a target animation. When we start a transition, sometimes we want to go to a specific point in the target based on some conditional stuff. I might be blending out of a walk cycle, and I might be blending out on the left foot, or might be blending out on the right foot. And maybe my target animation can support both for some reason. You know, it can handle, it maybe has a section in the front that handles a left foot, which then goes to a right foot, and then it stops or something. We can basically say, hey, in the target animation, I need you to start at sync period 1 or 2 or 3 or 50% through period 7. That is information in the graph that we can set up per transition. And we can basically have some flags saying, you know, match the sync interval. It's not a synchronized blend. It just says, we'll blend, but you need to start the target animation at this point. A very good example of where this is useful is start to cycles. So when we blend from a start animation, we basically are idle, we play a start, and then we end at a pose that matches the cycle. Depending where we blend out of that pose, we want to blend into the cycle at that specific point. But it's not a synchronized blend because there's nothing to synchronize. The two animations can't be synchronized together because the one is a cycle, the one is not. So what you want to do is you want to say, hey, when I blend out, I need you to start the cycle at interval 0, but match the percentage through, and you would have put an event in your start that's artificial, that basically says, this is my last frame cycle, that basically controls the start time of the next animation. I don't know if I explained that well enough. Maybe the next example will explain this a bit better. This is a bit of an artificial example, but imagine you have a jump, which is made up of two animations. You have the initial launch, which is like the boom off the ground in the air, and then you have like a landing that takes, let's say they made an animation takes 15 meters of distance. But that target could be anywhere between 5, or let's say between 1 and 15 meters, or maybe longer. So you need to now basically handle a massive amount of distance, but your animation's made to 50 meters. So what you can do is you can basically put some periods in that animation, and say, okay, sync period 0 covers the first 5 meters, 1 covers the next 5 meters, 2 covers the next 5 meters. And then based on the target, you will then have a transition that says, hey, transition me at the start of 0, or transition me into the start of 1, or transition me into the start of 2. Right? So you could kind of basically shortcut where in the animation you want to start by simply setting a transition start point with this sync track. So they're not necessarily just used for synchronization, they're also used for setting the start time, if that makes sense. I mean, you could solve this problem by making 3 animations, but it's 3 animations to maintain, and there are little tricks in here that you can kind of do. Any questions on the sync topic? So yeah, like that's kind of a use case for it. Mostly the start time is to handle those cases where you want to match a phase from one animation to a next animation, but you don't want to do a synchronized blend. But it can be used to handle like this sort of coverage. As I said, I'm conceptually, it's not a very hard problem. The code is maybe 100, 200 lines of code. I'm just surprised it's not more prevalent. I think Unreal now finally has some way to synchronize animations. I haven't looked into it too deeply, but it took them a while to get there. But again, in their case, they're not really deal with root motion, a bunch of other stuff. So they have different problems and they solve them in different ways. Okay, we're almost at the end. This thing grew a little bit out of control. Motion warping, the latest feature from Unreal 5, So this is, again, everything in this thing is a relatively simple complex that's been just made more complicated than it needs to be. So what it is, in a nutshell, is you take root motion, you modify it to reach a new endpoint. That's it. There's 2 ways to do this. You can do basic adjustments, that's frame to frame stuff, where you can overwrite the root motion delta or modify the root motion delta, or you can warp the whole root motion track. The basic version is you basically have an animation, you put a node in front of it that's like a procedural root motion node, you feed in the animation, you feed in some new inputs, and then that modifies the root motion coming out of the animation. So for example, I want to steer a walk cycle. The walk cycle is just a straight line animation, just walk straight. So what I want to do is I want to procedurally add rotation every frame based on the stick input. I want to keep all the forward momentum and the nonlinearity of the velocity coming from the anim driven, but I want to steer. So that node will basically take the root motion delta coming from the animation and apply an additional rotation. Additionally, you can add limits. You can say, hey, I want to take this root motion delta, but I want to say, I want to limit the angular velocity. I want to limit the linear velocity. So again, for the steering, you can put a limit there and say, do not steer more than, let's say, 360 degrees per second or something. Right? And so you can basically end up having a procedural modification to your anim driven. You kind of always need to. There's no such thing as pure anim driven unless it's a context of like you do a special move that then the player loses complete control and it just plays the animation, and at that point you have control. If you have control of the character and you're anim driven, you are procedurally modifying that thing some way or other. The other approach is warping. And basically all we do is we take that track and we warp it, be it stretch, modify, whatever, just to reach a new endpoint. And this is how things like parkour, interactions, attacks, and all that kind of stuff is done. In a lot of games, you see it. You see the character, let's say they want to open a door, but they're at a weird angle, and then they slide into position and then they interact with the door. That is kind of the warping. How it's done differs because in a lot of games, this is done purely by code where they basically just interpolate positions with the capsule. In some cases, you basically, when you're anim driven, you would actually modify the motion, like you have a jump climb in this scenario. You basically want to handle really tall objects, objects that are a bit further away, but at different heights. You know, you want some flexibility saying, I made one animation that covers one case, and I need to reuse that animation to cover multiple different scenarios. And that's what warping is fundamentally used for. Ooh, bad. Copy paste. Whoops. Let's hope it's not on every slide. So one thing to note here, if you look at the last version there, you'll notice that there's quite a bit of a gap between the wall and the character. Whereas in the first two, the gap is roughly the same. It's kind of small and stuff. And in some cases, we want that gap to be that distance off the wall, right? What we want is something like this, where we had this initial wide gap. That's not what the animation is made for, because maybe the feet touch the wall and there's a bit of kickoff while the character's like scrambling up. We still want that to have contact with the wall. We don't want it to float in space, even though he ends up at the right position at the end, right? So that's super important to kind of handle. And oh, fuck me. So how we do that is by basically, again, using our events and putting windows and saying, hey, I only want to allow translation in X and Y over this portion of the root motion. And I only want to allow translation in Z for this portion of the animation. Basically, you're marking up the animation saying, you know, modify it here this way and modify it here in this other way. Does that sort of make sense to everybody? Cool. Oh, sorry about this. I'm gonna kick myself afterwards. Additionally, what you could do is you could basically just say, hey, warp the whole thing, right? And then you get back to the original case. So we say, I don't really care how it's warped, just get me to the endpoint, I don't care. Maybe that animation is just like a superhero run, boing, in midair, and then, you know, clamp it to the wall. So you just don't care. It's all dependent on your use case. So as I said, we would use the events. It's not really alignment over time. That's kind of the more traditional approach, which kind of looks a bit slidey and stuff. This one is mostly, well, I'll explain it. It's more rigid, I think is a way to explain it. What we do is we basically calculate a target for the warp. Sometimes using the end of where the root motion ends you might not be what you want. For that climb, for example, the animation could be run, scramble up, hook, climb over, stand up, and step. They might have made that a single animation, including the climb up and the step over. You don't want to now pin the endpoint of the animation to the edge of the hang climb, right? That'll look super weird because he's going to climb mid-air and then walk and then end up literally on the edge. So what we end up doing is we add a helper bone, and this is something I covered earlier with these anchors, where we add an anchor. In the original animation, the animator will place the anchor at the edge of the object he's climbing, for example. And in their scene, they built the animation for a specific height, specific distance. So they place the anchor where they say, this is what I was climbing, this is what I expect it to be. In the game, what we do is we basically say, okay, I need to handle something where my anchor needs to be that point up there somewhere. I place the anchor at that position. We have a restriction that at least the first and last frame of the root motion track cannot be modified. Generally, we don't warp immediately and literally right up to the end. We always, 90% of the time, we're warping somewhere in between because For a lot of the complex movements, you can't warp the whole thing. You have to warp it in specific sections. So we'll basically say the start and the end, we know that there's some frames that are fixed. We will use the anchor as a reference point. We know where the start is because we have the character position, and the end point is relative to the anchor. So we basically plonk the anchor down, and then we put the end relative to the anchor, how it would be in world space. And this is the important thing, is that it's done in world space. So what do we do next? Well, I just explained this. Oops. But this is also a good point of why we wanted the root motion to start at the origin, because if it starts at 0, 0, we just say, hey, the character position, this is where the root motion starts. We don't have to do any additional manipulation. We just literally take the delta and apply it. Next thing we do, and I say it has to be done in world space. It can be done in character space. It doesn't need to take the world transform into account. It just needs to be within the same coordinate space, be it character or world. So we look at that setup. We have the initial bit at the start, we have the end bit at the end, and we say, okay, how much do I need to modify the animation to reach this? How much do I have to modify the root motion track? And how many sections do I have that need to be modified, and what are the modifications I need to apply to those sections? We can look at that. We'll do some calculations. The math is entirely up to you. There's no wrong or right way or whatever. That's completely like, depending on the situation, you can have different ways of solving it. You calculate intermediate targets for those sections, and then you put back any sections that are unmodified. So in the example we had before, you see we only have 2 sections that we're modifying, and we have a gap in between. So we'll calculate intermediate targets, and then we'll say, okay, we'll place this thing here because I want to maintain that offset from the wall, and I just want to have Z applied there. So I know what I have to do, and then I know where the unmodified piece has to end. I put it there, and now I have to solve the initial entry bit. And then once we solve that, we get our new root motion curve. And this is actually a new root motion curve. We don't modify the root motion in the animation. We basically just copy a new track, fill it out with our warped data, and that acts as a new root motion track. And so that root motion track is done in world space, and it basically gives us the world space path for the character to perform that movement. And that's important, which we're going to get to now. Now, I said that there's multiple ways to handle the warping. You can naively do it by simply just doing like the sort of DCC Maya approach of saying, I'm going to split my root motion track into components, and I'm going to have a translation X track, a translation Y track, a translation Z track, blah. And then I'm going to figure out I need to add 10 10 meters of offset over 50 frames on translation X. Well, I know how to do that. I just divide it and boom. If I want to, I can track the deltas of each frame on that track and say, well, this frame I move 2% of the total, this frame I move 4% of the total, this frame I move 2%, and apply that offset with that previous delta. So you would keep roughly the same nonlinearity. Basically, you're just stretching that track out. That's one approach. It works for translation kind of well. Rotation, you might split them into Euler angles, again, do that thing, but then you have maybe issues with shortest path rotations and stuff. Another approach is you would take the actual spline in 3D space, and then you would do spline manipulation by stretching and manipulating it, by trying to retain the original features of the graph. If it's got a wiggle, you try to keep the wiggle, but you stretch it. This is entirely up to you. I would suggest that you have multiple approaches. For example, the splitting into tracks works pretty well for some movements, like big jumps, rocket jumps, those kind of things. But when it comes to locomotion, like entries into interactable objects, smart objects, that kind of thing, you generally want maybe curve stretching. That tends to be kind of give you a more organic movement because the character will then follow a smoother path rather than what this track individual transforms will do. They'll get you to the right point, but how they get there. And this is where the art is. The concept is simple. The art is mostly in how do I calculate those intermediate sections and how that modification is done. And that's where the fancy stuff comes in. But again, if you want to do the most basic split into tracks and stuff, again, it's like a day or two of work and you're done. Would curve stretching on parkour look worse than splitting? It depends. It really depends. It depends on the movement. It depends on how the root motion is authored. It depends on what that movement is doing. If, for example, you have a very dirty movement, and what I mean by dirty is like it's scrambling, and it's like it's not a boing jump, and I'm at the top. It's like I'm scrambling up the wall, and it's like kind of jerky and stuttery, and I'm like scrambling, whatever. At that point, you probably want to try to maintain the root motion features. You probably want to try to maintain if there was a nonlinearity in the velocity. You want to try keep all of those things in the right ratios and just stretch it. But if the thing was like a run, jump, boing at the top, probably doesn't matter, right? Question, does somebody know if I can have authored root motion Unreal with Blender use? I don't know. I don't know too much. My knowledge of the Unreal Anim system has faded over time. As far as I know, it doesn't really matter how it's authored because you have to extract it in the engine. The root motion isn't coming in at import time. You're basically going to an animation, ticking a enable root motion, which then calculates some stuff. I think that's how it worked. I don't think the authoring tool has anything to do with the matter, but I might be wrong there, so don't quote me on that. When we have this, okay, so now we have this warped track, which is like the exact thing we need to do to get up to the top. We've done some cool math. The curves are super beautiful and everything's great. Well, there's two ways to follow that curve. And I call them inaccurate and accurate, and explain why. So inaccurate basically says, okay, I'm going to just say, this is my new root motion path. That's it. I'm going to forget that I have an original one. I'm going to just take this and I'm going to treat it like the original one. I'm going to take deltas, right? And at that point, coordinate space is irrelevant. It's a delta. Between one transform and the next, doesn't matter what space it's in. And so I treat it exactly the same way, and I just apply deltas, which means that I'm not guaranteed to reach the end. Because depending on the frame rate, I might skip between a curve section and just straight line it, right? And move less or more. I might hit a collision midway through and I've got to get blocked by it, and so on. So this is kind of more of a, hey, I wanted to get to some place. I don't really care if I exactly end up there because maybe it's an attack, maybe it's something else. Just try get me there, and then whatever happens, happens. So this is more useful for something like I want to warp a melee attack. The accurate version basically tries to lock the character onto the world space path of the warped track. And what it does is it says, okay, I know what frame you are in the animation. I know where you think you should be in world space according to that time in that track. Where are you now in world space? It has the character position in world space and says, okay, what is the delta that I have to apply this frame to get you to where you're supposed to be in world space? So the delta is not between subsequent frames on the root motion. It's between the character position in world space and where it should be in world space. So it's constantly being pulled to the right position onto that track. This is absolutely guaranteed to get you to follow that exact path and get you exactly where you're supposed to be and make sure this is. So this is really good for things like parkour moves, because it will follow that root motion exactly, and it'll make sure that like it's exactly the offset that it was calculated off the wall, and all your contacts maybe will work and stuff. Obviously, if it gets blocked, it's going to fight because it's going to try to be here. There's something in the way, and it's going to keep pushing. And if something else is pulling it or whatever's happening, it's going to keep accelerating because the target's going to keep moving and the delta per frame is going to grow. So the acceleration velocities per frame are going to grow as well. And that is a problem. You're going to end up with a lot of like shaking of the characters and shit. So what you want to do is you want to build in a switch for this. You want to basically specify on the warp saying, hey, if you're using accurate, I'm going to give you an error threshold. If you get outside of this error threshold for any reason, like you get more than like 10 centimeters off your position that you're supposed to be. At that point, you fall back to inaccurate. So we're going to keep following the move and stuff, but it's inaccurate. If you get blocked, you get blocked. And that's kind of it. So you need a kind of like, it's a fallback plan of this. And again, this is why I like the root motion stuff, because you have a lot of flexibility in how you can use it and how it can be leveraged to give you the best results possible. Additionally, your warps can be updated. Just because you calculated a warp doesn't mean you can't recalculate it. So let's say I started a melee attack and I have a longer warp period of like 7 frames or something. If the character's moving, I can recalculate the warp while I still have warp events or warp windows remaining. And what it's going to do is, as you carry on the animation, it's going to just warp from where you are in the animation to the target. Obviously, if the target moves too much, you're going to get some weird pops, because if the target's moving super fast and you start running out of the warp window, it's going to just like pop you. So again, this is something that can be used in the toolbox, generally can cause a lot of problems too, so you kind of want to avoid it. You don't want to have homing missile character, or maybe you do, depending on your game. You know, it's something that can be handled, and you can do it sometimes. So again, it can handle some degree of variation. So what we do is we basically, when we trigger a warped attack or something, we put a target, and then we limit how far that target can move. So we have a target and we have the character. So the character can move whatever we want, but this target is stuck within a zone that we know is feasible for an update. So we don't have too wide of a gap. So if we run it out to that warp window, we still end up roughly where we wanted to initially, and we don't pop somewhere, God knows where. Again, that was a system on top to solve this problem. Use cases differ. You need to do what you need to do in your game to make it best. Another less common use case is animation selection. I mentioned earlier that when you author the root motion, you can leverage that information to do stuff like selection of animations. You could say, hey, I need to get to this point with, what's a good example? Let's say I need to do a entry into a smart object or something, and I have a whole bunch of entry animations, some that take me, you know, they come in from an angle, some that are kind of far away, some that are super close, some that have the back turned or whatever. Based on the root motion of those animations, I can basically score them and say, what's the one that gets me closest to my end goal with some heuristics, and then pick that animation and then warp that animation, right? So it's not like motion match or anything. I'm just basically saying, find me the animation where the root motion most closely gets me to where I want to be and it looks sensible. And then I will warp that so I have the least amount of modification, the best, and I try to maintain as much of the animation integrity as I can. That's a kind of very common use case, and why, if you have authored root motion, makes it a simpler thing to kind of reason about. Secondly, in the old days when we did starts, we would basically animate starts to blend with one another. So what we would do is, and again, I'm going to act it out, so sorry for this. We would be standing straight up, and we would have like an animation that would start 45. We would have an animation that starts other 45, one that goes forward, another one that goes forward with the other leg. And then we would basically say, if I want to blend 30 degrees, I will blend the 0 and the 45 because they were made to blend. This puts a really like strict restriction on how the animations are made, how long they are, how much distance they covered, how the root motion is authored, a lot of the stuff. Because if they're not matched properly and you blend them, you're not going to get 30 degrees. You're going to get something else. Additionally, if we take this animation and say, okay, well, we're just going to steer it. We're going to take the 45 here and we're going to steer it 10 degrees left over the duration of the animation. That's not going to give you 30, right? That's going to give you a curved path, which might end up somewhere else, depending on the length of the animation, how much time, blah, right? And then on top of that, these days, what's very popular to do is that we don't have head-on idles. Our idles aren't straight anymore, right? They're not like this. They're often these super stylized, like bladed stances. So if I want to go right 45, it's just a straight shot. But if I want to go left, I basically have to open up and turn and step, right? So the length of the animations differ, the amount of steps differ, the timings differ. You can't blend these anymore, right? And you also can't provide like coverage for every angle under the sun. So one good way of handling this is to, again, leverage the warping by picking firstly what's sort of the best animation. Then what we can do most of the time, especially for starts, we want to rotate and then move, right? Because we're standing idle, and applying the rotation initially and then moving is less ugly than applying it during the move. Additionally, it gives you a more accurate result because you haven't moved. You're just rotating and you're going in the right angle. So what we do is we'll put a rotation event at the start of the animation. And then we'll say, hey, just warp it so that the endpoint of the animation doesn't need an anchor bone or anything, just so that the endpoint is at a 45-degree angle. So that where the character ends up and where the character starts, that angle is exactly 30, and we get exactly 30 degrees on the way out. And so for us, for example, in our game, we have a lot of warping going on all the time. It's one of the most frequently used tools, and it's happening all the time. And again, people might say, oh, it's expensive. It's not that expensive. You get a mem copy and you do a bunch of math, right? If you start going crazy of like things over time with integrals and math, and I mean, my solutions tend to be the most dumb things possible. So literally when I had to solve this the first time, I just said, okay, like what is literally the dumbest thing I can do is, well, I'll copy the track and I'll modify it. There, done, warping. Right. I saw other approaches that were dynamically warping per frame and tracking deltas and reading transforms, and it's kind of insane. This is also why I don't compress the root motion track. I don't want to pay the cost of decompression when I'm doing this. I just want to literally have the transforms. I can afford to pay for my 30, transforms. Just want to copy paste them and work with them super efficiently, super like fast, without having to now decompress, dequantize, whatever the fuck I need to do with this. And that's kind of the end of it. And I am so glad I split it because, oh my God, that's now almost 3 hours. I am so sorry for whoever sat through the whole thing. You guys must be exhausted. So any final questions on this topic? The next presentation will cover mostly the Anim graph and more integration into the game and how it's used in the game. It'll be a little bit, hopefully, shorter. Yeah, it probably will be shorter because it's a lot less topics. It's literally just an Anim graph. But yeah, there's a lot of detail on this and there's not a lot of information out there. So hopefully it helped people. It's basically a brain dump of years of kind of like messing with the stuff and a little bit of a rant. This topic tends to be made way more complicated than it needs to be, and I don't understand necessarily why. When I first started working with Morpheum, I got so scared initially because I remember starting to step through the code, and it was just, it looked like a rocket scientist had written it. It was insane. The graph was iterated through 5 times. They were using crazy math, and like they had a 2000 line 2-bone IK solver, and bone mask feathering was like thousands of lines of code, and they had like, it was insane, and it scared me. It literally scared me. I tried to look at the compression and I basically backed out of there super fast. I was like, okay, no, I'm too stupid to understand this. This is rocket science. And over the years of kind of having to build it myself and going through it and looking at how stuff is done, I'm starting to realize that what it seems to be is it's a lot of people being thrown in the deep end saying, make animation without having the time to iterate or knowing the domain and kind of just figuring it out as they go along. And as that happens, your first time you build something, you don't know the problem space, you don't understand it. So you build the most complex thing because you just don't know any better, and you think it needs to be complex, and you try to predict things, and you try to kind of say, okay, well, I'm going to handle every case under the sun. And I think that's the one benefit that I've had, which most people haven't, is I've had the chance to build the same system multiple times, but also have it trial by fire with animators over that time. And like that generally does give you an insight that is lacking from just being a maintainer of a system. I was able to basically build something, have people use it, see the profiles, see pain points in the workflows, and then on the next version, basically I'm starting from scratch. So I can basically flush all the bad decisions I made and strip it even further. And every time I do it, I keep losing more code because I realize it's not necessary. One of the Anim systems at UB was also a graph, and it had something insane like 30 blend nodes, right? Because they had, and it's because every time on every project, somebody says, I need a node that blends like blah. And some programmer doesn't know. And so he just builds what he's asked and delivers it. And then you have 7 nodes that do the same thing with slightly different names and completely different parameters and weird names on things, and nobody knows how anything works anymore. And it's this massive, massive thing of just craft that somebody has to maintain. Whereas, like in my case, I've realized over time that it's like, well, I need one blend node. Literally, my animation system, the stuff that we work with at work, has one blend node, which is a 1D blend, and that's it. It's a 1D range blend, and that's all we need. There's no other blends in the entire graph, and nobody's asking for any other blends. We have one transition, right? We have a super like reduced set of nodes, and it's a very simplistic thing, but it works. But it's primarily because I've had the luxury of redoing it, and I think a lot of places it's like people just built the first thing that came to mind and then just maintained it for 15 years. Yeah, gatekeeping. I don't think I've noticed much gatekeeping in animation, to be entirely honest. A lot of people are scared of it. And maybe that's kind of an abstract sort of gatekeeping where a lot of progs that I've talked to are like, no, animation is super scary. It's a lot of math. Like, I can't, I can't do it. It's terrifying. And it's like, it's not. I showed you the blending. It's a lerp and a slurp. The modification of the curve, it's not rocket science. It's just manipulating 3D transforms to reach a goal. It's IK, ragdoll, cloth. Yeah, those things can get complicated, but I mean, that's not necessarily animation per se. It's a part of it, but it's not the core, you know? Maybe it's that a lot of people think it's really hard and it's like domain. A lot of the problem is a lot of programmers still think of animation as how they used to do it 10, 15 years ago, especially engine programmers. And so they think it's like, well, we need to optimize blending and sampling and then we're done. It's like, whoa, you did like 1/10 of it. The complex part is how it's integrated into the game, how the logic runs, how the graph works, how all the synchronization and tooling and all of that works, and that needs to be efficient. Being like, oh, you optimized the blend, it's like, good job, and now your fucking graph takes 3 milliseconds. Congrats. You saved 0.01 microseconds on the blend, and we're still paying 3 milliseconds for the graph. It doesn't work that way. But yeah, it's like I hope to get more information out there. Once I do the dump of the Anim graph, at least that'll be most of my 10 years of knowledge, and then I can have that out of my system and be like, okay, there at least it's out there and it wasn't for nothing. But yeah, that was it. If anybody has any questions and stuff, you can always like poke me on Twitter or whatever. And hope it was useful. Hopefully in a couple of, I'm not going to promise a date, but a couple of weeks, maybe a month or two, I'll do the follow-up on this with the graph. And until then, thanks everybody that watched it, and have a great weekend.